Subscribe to the channel so you don't miss out on any of these videos. Imagine this: billions of galaxies scattered across the universe, each moving through an almost incomprehensible void. But what if I told you that these galaxies aren't just floating aimlessly? Instead, they're connected, woven together by a colossal, unseen network of structures that form what some scientists call intergalactic highways. These aren't highways like the ones we drive on, but vast, invisible streams of gas, dark matter, and gravitational forces that stretch for millions of light years. They guide the movement of galaxies, connect clusters, and may even hold the key to understanding the very structure of the cosmos. Sounds mind-boggling, right? Let's dive into this mystery of the universe and uncover the secrets of the intergalactic highways. To truly understand these highways, we first need to explore the concept of the cosmic web. The universe, when viewed on the largest possible scales, isn't random. Instead, it forms a web-like pattern, with galaxies, galaxy clusters, and superclusters linked together by filaments of dark matter and gas. These filaments are unimaginably massive, stretches of matter spanning millions of light years, but they're also incredibly diffuse. Imagine the faintest threads of spider silk stretched across an entire continent. That's what these structures would look like if we could see them with our eyes. But these highways aren't just passive structures. They play an active role in shaping the universe. They guide the motion of galaxies, pulling them along gravitational currents like leaves floating down a river. And they do this on scales so immense that it's hard for us to grasp. A single filament can connect multiple galaxy clusters, each containing thousands or even millions of galaxies. The highways effectively act as bridges, linking these clusters and allowing matter to flow between them. How do we know these structures exist? Scientists have spent decades piecing together evidence using powerful telescopes and simulations. The cosmic web itself is largely invisible, but it leaves subtle fingerprints on the universe. For example, when light from distant galaxies passes through these filaments, it gets slightly distorted, a phenomenon known as gravitational lensing. By studying these distortions, astronomers can map out the shape and structure of the intergalactic highways. Another way scientists study the cosmic web is by looking at how galaxies are distributed. Galaxies aren't spread evenly across the universe. Instead, they clump together in clusters, connected by filaments, with vast empty regions called voids in between. This pattern didn't happen by chance. It's the result of billions of years of gravitational interactions, with dark matter playing a central role. Dark matter, though invisible and still not fully understood, makes up most of the mass in the universe. Its gravitational pull is what forms the scaffolding of the cosmic web, shaping where galaxies can and can't exist. Let's pause for a second and consider just how strange this is. We're talking about a structure so vast it defies imagination, made of a substance we can't see or directly detect. Yet it governs the movement of entire galaxies and dictates the structure of the universe itself. It's as if we're ants crawling on the surface of a giant spider web, unable to see the web but still bound by its design. What's even more fascinating is that these highways don't just guide the motion of galaxies. They also transport matter. Streams of gas flow along the filaments, feeding galaxies and clusters. This process is crucial for galaxy formation. Galaxies need a steady supply of gas to form new stars, and the intergalactic highways act as cosmic supply lines, delivering this gas across vast distances. Without these highways, many galaxies would have run out of gas long ago, becoming barren and lifeless. Now, here's where things get really intriguing. The cosmic web isn't static. It's constantly evolving. Over billions of years, filaments stretch, shift, and sometimes even collapse, driven by the expansion of the universe and the pull of gravity. This dynamic nature adds another layer of complexity to an already mind-blowing phenomenon. It's as if the highways themselves are alive, changing and adapting over cosmic timescales. But there's more. The study of intergalactic highways could also help us solve one of the biggest mysteries in astrophysics: the nature of dark matter. Since dark matter forms the backbone of the cosmic web, understanding these structures could provide crucial insights into what dark matter actually is. Right now, dark matter is one of the greatest enigmas in science. We know it exists because of its gravitational effects, but we don't know what it's made of. By studying the cosmic web in greater detail, scientists hope to uncover clues about this elusive substance. What about the role of dark energy? While dark matter pulls the cosmic web together, dark energy works in the opposite direction, driving the expansion of the universe. This tug-of-war shapes the highways and determines how they evolve over time. Some researchers believe that studying these structures could help us better understand dark energy and its impact on the cosmos. And then there's the question of life. If galaxies are connected by highways of gas and dark matter, could this network also play a role in the distribution of the ingredients for life? Some scientists speculate that the flow of matter along the cosmic web could spread elements like carbon and oxygen, key building blocks of life, across the universe. It's a tantalizing idea, one that adds a whole new dimension to the mystery of intergalactic highways. The more we learn about these structures, the more questions arise. How did they form in the first place? What role did the Big Bang play in shaping the cosmic web? Could there be undiscovered phenomena hiding within these massive filaments? And what does this all mean for our understanding of the universe? These questions are not just intellectual curiosities. They cut to the heart of how the universe operates. To understand the origins of the intergalactic highways, we must rewind the clock to the earliest moments of the cosmos, just after the Big Bang. At that time, the universe was a hot, dense, and nearly uniform sea of particles. But even in this uniformity, tiny fluctuations in density existed, regions where there was just a bit more matter than elsewhere. These fluctuations, amplified by gravity over billions of years, eventually grew into the structures we see today: galaxies, clusters, and the cosmic web that connects them. Dark matter played a pivotal role in this process. Because it doesn't interact with light or ordinary matter in the way we're familiar with, dark matter began clumping together early in the universe's history, forming massive halos. These halos became the gravitational anchors for gas and dust, which eventually coalesced into galaxies. The highways we see today are essentially the remnants of this early cosmic scaffolding, with dark matter providing the framework and ordinary matter filling in the gaps. But here's where things get even more mind-blowing. The cosmic web isn't uniform. It has regions of extreme density, like galaxy clusters, and vast, empty voids where almost no matter exists. These voids can span hundreds of millions of light years, creating some of the most desolate places in the universe. Yet, even in these voids, faint whispers of the cosmic web can sometimes be detected. Scientists have found that these voids aren't entirely empty. They contain tenuous streams of gas and dark matter, connecting to the larger highways that surround them. The tools scientists use to study the cosmic web are equally fascinating. One of the most effective methods involves mapping the distribution of galaxies across the sky. By observing millions of galaxies and plotting their positions in three-dimensional space, researchers can create detailed maps of the web's structure. These maps reveal the filaments and nodes that make up the highways, as well as the vast voids in between. Another technique involves studying the light from distant quasars, extremely bright objects powered by supermassive black holes. As this light travels through the universe, it passes through the gas in the cosmic web, leaving behind a series of absorption lines in its spectrum. By analyzing these absorption lines, scientists can infer the density and composition of the gas, providing a glimpse into the intergalactic highways. But while we've made incredible progress in understanding these structures, there's still so much we don't know. For example, recent observations suggest that the gas in the cosmic web may be hotter than previously thought. This heat could come from shock waves generated as galaxies and clusters collide and merge, but the exact mechanisms are still a mystery. Understanding this heat could give us new insights into the dynamics of the web and the processes that shape it. The cosmic web also raises profound philosophical questions. If the universe is connected by these vast highways, what does that mean for our place in it? Are we just tiny, insignificant specks in a vast, interconnected network? Or is there a deeper meaning to the web structure, one that we've yet to uncover? These questions touch on the very nature of existence, challenging us to think about the universe in entirely new ways. And then there's the possibility of using the cosmic web as a tool for exploration. Some researchers have speculated that advanced civilizations, if they exist, might use the highways to travel between galaxies or clusters. While this idea is purely theoretical, it's not entirely out of the realm of possibility. After all, the cosmic web represents the most efficient pathways through the universe, minimizing the energy needed to traverse vast distances. If we ever develop the technology to travel between galaxies, understanding these highways could be crucial. As we continue to explore the intergalactic highways, one thing is clear: they are far more than just abstract structures. They are the lifelines of the universe, connecting everything from the smallest galaxies to the largest clusters. They shape the flow of matter, influence the formation of stars and planets, and provide a glimpse into the fundamental forces that govern the cosmos. The study of the cosmic web is still in its infancy, but the potential for discovery is immense. With new technologies like the James Webb Space Telescope and next-generation simulations, we're on the brink of uncovering even more secrets about these mysterious highways. Who knows what we'll find as we peer deeper into the web's structure? Perhaps we'll discover new types of matter, unknown physical phenomena, or even evidence of extraterrestrial life. The more we learn, the more the universe seems to invite us to ask bigger questions. What's beyond the cosmic web? Are there other webs, other universes, connected in ways we can't yet comprehend? And if so, how do they fit into the grander scheme of existence? If we consider the idea of multiple universes, often referred to as the multiverse theory, the cosmic web might only be a small piece of an even larger puzzle. Imagine if every web-like structure we observe in our universe were just one strand in a far more complex and incomprehensible multiversal fabric. Could these intergalactic highways connect not just galaxies and clusters but entire universes? This possibility takes the mystery of the cosmic web to a completely new level and hints at a reality that transcends anything we've imagined. But before we venture too far into speculation, let's circle back to what we know about the observable universe. The cosmic web doesn't just connect galaxies and clusters, it also seems to influence the properties of the galaxies it touches. Studies have shown that galaxies located along the filaments tend to form stars at higher rates compared to those in more isolated regions. Why? It's likely due to the steady stream of gas flowing along these intergalactic highways, which serves as raw material for star formation. Essentially, the cosmic web acts as a delivery system, providing galaxies with the resources they need to grow and thrive. However, not all galaxies benefit equally from this flow of resources. Some galaxies, especially those near massive clusters, can experience something known as strangulation. In these cases, the gravitational pull of the cluster strips away the galaxy's gas, leaving it unable to form new stars. This interplay between growth and suppression adds another layer of complexity to the role of the cosmic web in shaping the universe. There's also the question of how these highways evolve over time. Observations of the early universe suggest that the cosmic web looked very different billions of years ago. The filaments were less defined, and the clusters they connect were much smaller. Over time, gravity has amplified these structures, pulling matter into the filaments and clusters, making them more pronounced. But this process isn't uniform. In some regions, the filaments are thinning out as the universe expands, creating even larger voids. This evolution is a delicate balance between the pull of gravity and the push of dark energy, which drives the universe's expansion. One of the most exciting developments in studying the cosmic web is the use of advanced simulations. Scientists create massive computer models that replicate the formation and evolution of the universe, starting from the Big Bang. These simulations incorporate our current understanding of physics, including the effects of dark matter and dark energy, to generate a virtual universe that closely resembles the real thing. By comparing these simulations to actual observations, researchers can test theories about the cosmic web and refine their models. But these simulations also raise new questions. For example, some models predict the existence of smaller, fainter filaments that are difficult to observe with current technology. These so-called missing links in the cosmic web could play a crucial role in connecting isolated galaxies and clusters. Finding these hidden structures will require even more sensitive instruments and creative observational techniques. Speaking of hidden structures, let's talk about dark matter again. While we know it forms the backbone of the cosmic web, its true nature remains one of the greatest mysteries in science. Some theories suggest that dark matter might be made up of exotic particles that interact only through gravity, while others propose entirely new forces of nature. Understanding dark matter is critical not just for studying the cosmic web but for understanding the universe as a whole. After all, if dark matter didn't exist, the intergalactic highways we're talking about wouldn't exist either. And what about the role of ordinary matter, the stuff we're familiar with, like gas and dust? While dark matter forms the framework of the cosmic web, ordinary matter is what makes it visible. When gas flows along the filaments, it can become hot enough to emit X-rays or ultraviolet light, which we can detect with telescopes. These emissions provide a way to map the highways and study their properties. Interestingly, some researchers believe that much of the so-called missing baryonic matter in the universe, ordinary matter that we know should exist but haven't been able to find, might be hiding in the cosmic web. If true, these highways could help solve one of the longest-standing puzzles in cosmology. As we piece together the puzzle of the cosmic web, it's impossible not to marvel at the sheer scale of it all. These intergalactic highways span distances that dwarf anything we can comprehend, yet they play a direct role in shaping the galaxies, stars, and planets that make up the universe. They're a reminder that even in the vast emptiness of space, everything is connected. But perhaps the most mind-bending aspect of the cosmic web is what it suggests about the nature of reality itself. The web's intricate, interconnected structure seems almost too elegant to be the result of random chance. Could it be evidence of some underlying order or design in the universe? Or is it simply a natural consequence of the laws of physics playing out on the largest scales? Whatever the answer, one thing is clear: the study of intergalactic highways is far from over. With each new discovery, we're reminded of how much there is still to learn about the universe and our place within it. The cosmic web is not just a physical structure, it's a gateway to some of the deepest questions we can ask. And as we continue to explore these highways, who knows what incredible revelations await? If we return to the core idea of the cosmic web being a highway system, it's worth asking how these intergalactic connections came to be so intricately woven. The forces that govern the web's formation, gravity, dark matter, and dark energy, are like invisible engineers shaping the universe. Gravity pulls matter together to form clusters, filaments, and nodes. Dark matter, with its mysterious and pervasive influence, acts as the scaffolding that guides ordinary matter into these structures. Meanwhile, dark energy counters this by pushing the universe apart, stretching and thinning some of the filaments, while intensifying others. The interplay of these forces results in a dynamic, ever-changing network. As galaxy clusters move along the filaments, they reshape the web, influencing its structure and evolution. This fluidity makes the cosmic web not just a static map but a living, breathing system that evolves over billions of years. What's particularly fascinating is how the cosmic web mirrors patterns found in other natural systems. The structures of intergalactic highways, for example, resemble neural networks in the human brain. Both are systems designed to maximize efficiency, distributing resources or information across vast distances. This similarity is not just superficial. Some scientists have explored whether universal principles govern the emergence of these patterns, suggesting that the universe, in some ways, might think or organize itself in ways we don't yet understand. But while these parallels are intriguing, the cosmic web scale is incomprehensibly larger. If we consider just one filament of the web, it might span millions of light years, connecting clusters that each contain thousands of galaxies. Within these galaxies are billions of stars, many of which host planetary systems. The sheer number of celestial objects connected by these highways boggles the mind. Now, let's shift to a more speculative but equally thrilling idea. Could these highways be utilized for cosmic travel? If advanced civilizations exist, and some astronomers argue that the numbers strongly favor this, they might use the intergalactic highways to traverse the universe. By aligning with the gravitational and dark matter pathways of the cosmic web, these hypothetical civilizations could reduce the energy required to cross vast distances. Imagine a spacecraft capable of harnessing the subtle flows of gas and energy within a filament, essentially riding the current of the cosmic web. This concept isn't entirely unlike how humans use ocean currents for efficient sea travel. Could these highways serve as cosmic trade routes or even channels for intergalactic communication? While this remains in the realm of science fiction, the underlying physics suggests it's not impossible. The cosmic web also serves as a lens for understanding the distribution of matter in the universe. Astronomers often refer to the bias of galaxies, meaning that galaxies don't form randomly but are influenced by the density of the cosmic web. This distribution helps us understand why some regions of the universe are rich in galaxies while others are nearly empty voids. These voids, while seemingly barren, are just as important as the filaments. They act as the negative space that shapes the web, emphasizing its filaments and nodes. One particularly compelling area of research involves the interactions between the cosmic web and supermassive black holes. These black holes, found at the centers of most galaxies, can influence the flow of gas within the filaments. As black holes consume matter, they release enormous amounts of energy in the form of jets and winds, which can heat the surrounding gas and alter its movement. This feedback loop connects the smallest scales of astrophysics, black holes and star formation, with the largest structures in the universe, the cosmic web. Another intriguing aspect of the intergalactic highways is their role in the chemical evolution of the universe. As gas flows along the filaments, it carries with it the building blocks of life, elements like carbon, oxygen, and nitrogen that were forged in the cores of stars. These elements are distributed across the universe, seeding new galaxies and planetary systems with the materials necessary for life. Without the cosmic web, the universe might lack the interconnectedness needed to spread these vital elements far and wide. Yet, for all we know about the cosmic web, much remains hidden. The faintest filaments, composed of diffuse gas and dark matter, are incredibly difficult to detect. Researchers are developing new observational techniques, such as using radio telescopes to map hydrogen gas or leveraging the gravitational lensing effect to study dark matter distribution. These methods promise to reveal even more about the highways that crisscross the universe. The cosmic web also provides a unique testing ground for fundamental physics. By studying how the web evolves, scientists can test theories about dark energy, the mysterious force driving the universe's expansion. The way the filaments stretch and thin over time offers clues about the properties of dark energy and whether it changes over time. This research could revolutionize our understanding of the universe's ultimate fate. As we delve deeper into the intergalactic highways, we're also uncovering clues about the earliest moments of the universe. The cosmic microwave background, a faint glow left over from the Big Bang, contains subtle imprints of the density fluctuations that eventually grew into the cosmic web. By studying these imprints, scientists can trace the web's formation back to its origins, gaining insights into the fundamental processes that shape the cosmos. Ultimately, the intergalactic highways of the cosmic web are not just a physical phenomenon, they're a cosmic story. They tell us about the universe's past, its present, and possibly its future. They connect the smallest particles to the largest structures, showing us that everything in the universe is part of a vast, interconnected whole. And while we've made incredible strides in understanding the cosmic web, the journey is far from over. Each new discovery adds another layer to this intricate tapestry, deepening our appreciation for the complexity and beauty of the universe. The intergalactic highways remind us that, no matter how vast and empty space may seem, it is a place of profound connection, where everything is linked in ways we are only beginning to comprehend. The cosmic web, with its intergalactic highways of dark matter and gas, offers a profound lens through which we can examine not just the physical universe but also our philosophical and existential place within it. It is a structure of unimaginable scale, yet its essence is rooted in the same fundamental principles that govern the smallest particles. This interconnectivity raises questions about the nature of the universe and whether its design is purely coincidental or follows some deeper, intrinsic logic. Let's delve into the philosophical implications of the cosmic web. If these highways represent the scaffolding of the universe, are we looking at a purely physical phenomenon, or is there something more profound? Many have pondered whether the universe operates under a set of universal principles that naturally lead to these intricate, web-like patterns. The cosmic web seems almost too elegant and efficient to be a product of randomness, leading some to consider whether it hints at an underlying order, or even intent. This idea has sparked discussions among scientists, philosophers, and theologians alike. For example, the anthropic principle suggests that the universe is structured in a way that allows for the existence of life because, if it weren't, we wouldn't be here to observe it. The cosmic web, by efficiently distributing matter and energy, could be seen as a critical factor in creating conditions suitable for galaxies, stars, and planets, elements necessary for life as we know it. However, this efficiency also raises the question, is the universe fine-tuned for life, or is life simply an emergent property of a universe governed by natural laws? The cosmic web, with its intricate highways and connections, provides a fascinating backdrop for these debates. It's a reminder that the universe operates on scales so vast and complex that our understanding, though ever expanding, is still in its infancy. On a more practical level, the cosmic web offers a roadmap for exploring the universe. Future generations of telescopes, such as the upcoming James Webb successors or ground-based observatories like the Extremely Large Telescope, will enable us to study the web in unprecedented detail. These instruments will help us map the faintest filaments, uncover the properties of dark matter and dark energy, and perhaps even detect signals from early galaxies forming within the web. One particularly exciting possibility is using the cosmic web as a guide to find potentially habitable exoplanets. Regions of the web that are rich in gas and star formation could harbor galaxies with a higher likelihood of hosting life-supporting planets. By focusing our searches on these areas, we might increase our chances of finding other worlds like Earth. The search for life also ties into the concept of cosmic interconnectedness. If life exists elsewhere in the universe, it would have emerged within the same cosmic web that connects us. This realization is humbling. It places humanity within a larger framework of cosmic evolution, suggesting that we are not isolated but part of a vast, interwoven tapestry. But the cosmic web's implications don't stop at life. Its very structure challenges our understanding of space and time. The web's filaments and nodes are dynamic, constantly evolving as the universe expands. This evolution raises questions about the ultimate fate of the cosmic web. Will the filaments continue to thin and stretch, leading to a universe dominated by vast voids? Or will gravity eventually overcome dark energy, causing the web to collapse back into dense regions? These scenarios, often referred to as the Big Freeze, or the Big Crunch, represent two possible endings for the universe, each shaped by the delicate interplay of forces within the cosmic web. Another area of intrigue is how the cosmic web might relate to quantum mechanics. On the smallest scales, particles exhibit behavior that seems random and probabilistic, yet the cosmic web, shaped by billions of years of gravitational interactions, appears ordered and deterministic. Bridging this gap, understanding how the universe transitions from quantum chaos to cosmic order, is one of the greatest challenges in modern physics. The cosmic web could hold clues to this transition, acting as a bridge between the microscopic and macroscopic realms. One hypothesis that attempts to unify these scales is the concept of holography. According to this idea, the entire universe might be a hologram, with all the information contained within it encoded on a lower-dimensional surface. If true, the cosmic web could be a manifestation of this encoding, representing the shadow of a deeper, more fundamental reality. While this idea remains speculative, it underscores the cosmic web's potential as a key to unlocking the universe's deepest secrets. As we reflect on the cosmic web, it's impossible to ignore its aesthetic beauty. The images and simulations of these intergalactic highways, with their glowing filaments and vibrant nodes, evoke a sense of wonder and awe. They remind us of the universe's complexity and the sheer scale of what lies beyond our world. For many, these visuals are more than just scientific data. They are a source of inspiration, a reminder of the infinite possibilities that await us in the cosmos. And yet, despite all we've learned, the cosmic web remains a frontier of mystery. Each filament, each node, holds secrets waiting to be uncovered. Whether it's the nature of dark matter, the role of dark energy, or the potential for life elsewhere, the web challenges us to think bigger, to question more deeply, and to push the boundaries of what we know. The intergalactic highways of the cosmic web are not just a physical phenomenon, they are a symbol of humanity's insatiable curiosity. They remind us that, no matter how much we discover, there will always be more to learn. The universe is vast, complex, and endlessly fascinating, and the cosmic web is one of its most intricate and captivating features. As we continue to explore these highways, we are not just uncovering the secrets of the cosmos, we are discovering our place within it. The vast cosmic web connects galaxies, clusters, and superclusters in an intricate, almost poetic design, but its influence extends beyond mere physical connections. It shapes the very nature of the universe, dictating how matter is distributed, how galaxies evolve, and even how time and space behave on a cosmic scale. As we continue to explore these intergalactic highways, our understanding of fundamental cosmic principles deepens, revealing layers of complexity that challenge and inspire human ingenuity. One of the most intriguing aspects of the cosmic web is its role in galaxy formation and evolution. Galaxies are not randomly distributed, they are profoundly influenced by the dense nodes and filaments of the web. These highways of gas and dark matter funnel material toward nodes, where massive galaxy clusters reside. This process often triggers bursts of star formation, creating vibrant, active regions of cosmic activity. However, not all galaxies thrive in this environment. The dense regions of the cosmic web can also lead to galaxy interactions and mergers. These events dramatically reshape galaxies, transforming their structures, altering their star formation rates, and sometimes even quenching their ability to form stars altogether. For example, galaxies within the dense cores of clusters often experience strangulation, where their supply of gas is stripped away by the cluster's hot intracluster medium. This process can lead to the formation of red and dead galaxies, those that have exhausted their star-forming potential. The cosmic web also plays a crucial role in the distribution of dark matter, a mysterious substance that makes up about 27% of the universe's total mass energy content. Dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its presence can be inferred through its gravitational effects. The cosmic web is primarily composed of dark matter, with baryonic, normal, matter following its scaffolding. This dark matter framework acts as a gravitational blueprint, guiding the formation of galaxies and clusters. Advanced techniques like gravitational lensing have allowed astronomers to map the distribution of dark matter within the cosmic web. By observing how light from distant galaxies is bent and distorted by the gravitational influence of dark matter, researchers can create detailed maps of these hidden structures. These studies have confirmed that dark matter dominates the mass of the web, providing the gravitational glue that holds it together. Another fascinating aspect of the cosmic web is its connection to cosmic voids, vast, empty regions of space that lie between the filaments. These voids are not entirely empty. They contain low-density gas, a few galaxies, and dark matter. However, their properties are strikingly different from the dense regions of the web. Void galaxies tend to be smaller, more isolated, and less evolved, providing a stark contrast to their counterparts in crowded clusters. Cosmic voids are also important for studying dark energy, the mysterious force driving the accelerated expansion of the universe. By analyzing how the large-scale structure of the cosmic web, including its voids, changes over time, scientists can gain insights into the properties of dark energy. This research is crucial for understanding the universe's ultimate fate, whether it will continue to expand forever, slow down, or collapse in a big crunch. The cosmic web's role as a cosmic highway extends beyond the distribution of matter. It may also serve as a conduit for the exchange of energy and information across vast distances. Some theories suggest that energetic particles, such as cosmic rays, could travel along the filaments, connecting galaxies and clusters in ways we are only beginning to understand. This possibility opens up new avenues for studying high-energy astrophysical phenomena and their interactions with the web structure. One of the most tantalizing questions about the cosmic web is whether it could play a role in the search for extraterrestrial intelligence. If advanced civilizations exist elsewhere in the universe, they might use the natural highways of the web to facilitate interstellar or intergalactic travel. The filaments, rich in gas and potentially hosting stars and planets, could serve as stepping stones for long-distance exploration. While this idea remains speculative, it underscores the cosmic web's potential as a key to unlocking the mysteries of the universe. Moreover, the cosmic web challenges our understanding of gravity and the laws of physics on large scales. While Einstein's general theory of relativity provides an excellent framework for understanding gravity, the behavior of the cosmic web, particularly in relation to dark matter and dark energy, suggests that there may be gaps in our knowledge. Some scientists propose modifications to gravity, such as theories of modified Newtonian dynamics, MOND, or scalar tensor vector gravity, SDVG, to explain the web's properties. These alternative theories aim to reconcile the observed behavior of the web with the limitations of our current models. The cosmic web also offers a unique perspective on the early universe. The filaments and nodes we see today are the result of billions of years of evolution, but they originated from tiny quantum fluctuations in the primordial universe. These fluctuations, amplified by inflation, seeded the formation of the web's large-scale structure. By studying the web, we can trace the universe's history back to its earliest moments, gaining insights into the processes that shaped its evolution. Perhaps one of the most profound implications of the cosmic web is its role in uniting the cosmos. The web's interconnectivity mirrors the interconnectedness of all things, from the microscopic to the macroscopic. It serves as a reminder that the universe, despite its vastness, operates as a single, cohesive system. This realization has profound philosophical and existential implications, challenging us to rethink our place in the cosmos and our relationship with the universe. As we continue to explore the cosmic web, we are not just uncovering the secrets of the universe, we are also uncovering the depths of our own curiosity and ingenuity. The web is a testament to the power of science and human imagination, a reminder that the universe is a vast, complex, and endlessly fascinating place. Its highways connect not just galaxies but also generations of explorers, thinkers, and dreamers who seek to understand the cosmos and our place within it. The study of the cosmic web is a testament to humanity's boundless curiosity and determination to decode the universe's mysteries. Its significance extends beyond the purely scientific, as it touches on deeper questions about existence, connection, and the nature of reality. As our understanding grows, so too does our appreciation for the universe's intricate design and the forces that bind it together. One of the most fascinating aspects of the cosmic web is its ability to link phenomena across scales. The filaments, stretching across millions of light years, represent structures on a scale far beyond human comprehension. Yet, their behavior and formation are governed by the same physical laws that apply to smaller, more familiar systems. This scalability is a hallmark of the universe, where fundamental principles manifest in diverse and unexpected ways. The filaments themselves are not static, they are dynamic, evolving structures. Over billions of years, they have stretched, twisted, and merged under the influence of gravity and the expansion of the universe. Their evolution is a delicate interplay between the forces of attraction, which pull matter together, and the forces of expansion, which drive it apart. This balance is critical to understanding the universe's large-scale structure and its future. Within these filaments, the flow of gas plays a crucial role in shaping galaxies and clusters. The gas within the filaments is often in a diffuse, hot state, ionized by the intense radiation from nearby stars and quasars. This intergalactic medium serves as a reservoir for galaxy formation, feeding star-forming regions and contributing to the growth of massive galaxies over time. Understanding the properties of this gas, such as its temperature, density, and chemical composition, is key to piecing together the puzzle of galaxy evolution. Observing the cosmic web directly presents significant challenges. Most of its structure is composed of dark matter, which does not emit or interact with light in any detectable way. However, advances in observational techniques have allowed scientists to infer the web's presence through indirect means. For instance, gravitational lensing, a phenomenon where massive objects bend and magnify the light from distant sources, has provided a powerful tool for mapping the distribution of dark matter. These maps reveal the intricate web of filaments and nodes that make up the universe's scaffolding. Another method of studying the web is through the absorption lines in the spectra of distant quasars. As light from these bright, energetic objects travels through the universe, it passes through the gas in the filaments. This gas absorbs specific wavelengths of light, leaving characteristic fingerprints in the quasar's spectrum. By analyzing these absorption lines, astronomers can determine the composition, temperature, and density of the gas, providing valuable insights into the properties of the web. Recent breakthroughs in computational simulations have also revolutionized our understanding of the cosmic web. These simulations use supercomputers to model the behavior of matter and energy on a cosmic scale, starting from the conditions of the early universe. By comparing these models with observations, scientists can test theories about the formation and evolution of the web. These simulations have revealed stunningly detailed structures, showing how galaxies and clusters form at the intersections of filaments, and how voids expand and evolve over time. The cosmic web's role in the universe's energy distribution is another area of active research. The web acts as a vast network for transferring energy between different regions of space. Energetic events, such as galaxy collisions or supernova explosions, can send shockwaves rippling through the filaments, heating the gas and triggering further star formation. This interplay of energy and matter creates a feedback loop that shapes the structure and behavior of the web over time. Moreover, the cosmic web provides a framework for understanding the universe's overall geometry and topology. Its interconnected filaments and nodes form a three-dimensional network that spans the observable universe. By studying the web's large-scale structure, scientists can infer critical information about the universe's shape, its rate of expansion, and the influence of dark energy. This research has profound implications for cosmology, as it helps refine our models of the universe and its ultimate fate. The cosmic web is also a rich testing ground for alternative theories of gravity and cosmology. While the standard model of cosmology, based on general relativity and the lambda-CDM model, explains many aspects of the web, there are still unanswered questions. For instance, the nature of dark matter and dark energy remains elusive, and some observations suggest discrepancies that may point to new physics. Exploring these alternative theories within the context of the web could provide clues to these fundamental mysteries. One of the most exciting frontiers in cosmic web research is the study of its connection to black holes and active galactic nuclei, AGN. These powerful engines of radiation and matter outflows are often found at the centers of massive galaxies within the web's nodes. Their interactions with the surrounding environment, including the filaments, can have far-reaching effects on galaxy formation and the distribution of matter. For example, jets from AGN can heat the gas in the filaments, suppressing star formation and altering the dynamics of the web. Additionally, the cosmic web may hold the key to understanding the origins of magnetic fields in the universe. Observations suggest that the web's filaments are threaded with weak magnetic fields, which could have been amplified over time by cosmic turbulence and the motion of charged particles. These magnetic fields play a role in guiding the flow of gas and influencing the behavior of cosmic rays, adding another layer of complexity to the web's dynamics. The philosophical implications of the cosmic web are equally profound. Its interconnected nature challenges our perception of individuality and isolation, reminding us that everything in the universe is part of a greater whole. The web's vastness and complexity inspire awe and humility, prompting us to reflect on our place in the cosmos and our responsibility as stewards of our small corner of the universe. As we continue to unravel the mysteries of the cosmic web, we are embarking on a journey that transcends the boundaries of science. It is a journey of discovery, connection, and wonder, a testament to the human spirit's unyielding quest to understand the universe and our role within it. The cosmic web study has ushered in new ways of thinking about the universe's interconnectedness, sparking interest not only among scientists but also philosophers, artists, and the general public. Its intricate structure serves as a metaphor for unity and interdependence, drawing parallels between the vast cosmos and systems closer to home, like neural networks in the brain or social systems among humans. This interconnectedness speaks to the idea that no part of the universe exists in isolation, a notion that challenges deeply ingrained ideas about separateness. One particularly captivating aspect of the cosmic web is its apparent universality. Despite spanning billions of light-years and containing unimaginable amounts of matter, its patterns echo familiar forms seen in nature. From the branching of trees to the delicate structure of a spider's web, the cosmic web's filaments bear a striking resemblance to many systems governed by physical laws. This phenomenon, known as self-similarity, suggests that certain organizing principles may be universal, operating at vastly different scales. Delving deeper into its formation, we find that the cosmic web structure is shaped by the interplay between gravity and the universe's initial density fluctuations. These fluctuations, seeded during the inflationary epoch just after the Big Bang, provided the framework upon which the web formed. As matter clumped together under gravity's influence, filaments grew, connecting the densest regions, which eventually became galaxy clusters. Over billions of years, these processes created the vast, interconnected network we observe today. One of the more mind-bending implications of the cosmic web lies in its role as a map of the universe's history. By studying the distribution and composition of matter within the web, scientists can trace the universe's evolution from its infancy to its current state. The web acts as a kind of cosmic fossil record, preserving evidence of the conditions and events that shaped the cosmos over time. Recent advancements in observational technology have allowed astronomers to explore the cosmic web in unprecedented detail. Instruments like the James Webb Space Telescope, JWST, and large-scale surveys such as the Sloan Digital Sky Survey, SDSS, have provided high-resolution data on the distribution of galaxies and gas within the web. These observations have confirmed many theoretical predictions while also revealing unexpected complexities, such as variations in filament thickness and density. For example, researchers have discovered that some filaments are enriched with heavy elements, materials forged in the hearts of stars and distributed through supernova explosions. This enrichment suggests that the cosmic web is not a static structure but a dynamic environment where galaxies interact with their surroundings, exchanging gas and elements. Such findings highlight the web's role as a conduit for material and energy, shaping the evolution of galaxies and the larger universe. Another exciting development in cosmic web research is the study of its voids, vast, empty regions that account for much of the universe's volume. These voids are not merely areas devoid of matter, they are key to understanding the web's structure and dynamics. By analyzing the shapes and distributions of voids, scientists can gain insights into the forces that have sculpted the universe on the largest scales. Moreover, voids serve as natural laboratories for testing theories about dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy's influence on the cosmic web is one of the most profound mysteries in modern cosmology. While its exact nature remains unknown, it is believed to exert a repulsive force that counteracts gravity, shaping the web's large-scale structure. Understanding how dark energy interacts with the web is crucial for unraveling its role in the universe's ultimate fate. Will the web continue to expand and stretch, or will it eventually collapse under its own weight? These questions lie at the heart of contemporary astrophysics. The relationship between the cosmic web and dark matter is equally intriguing. While dark matter makes up most of the web's mass, its properties and interactions remain shrouded in mystery. Scientists are exploring various hypotheses about the nature of dark matter, from weakly interacting particles to exotic forms of matter like axions. By studying how dark matter shapes the web's structure and dynamics, researchers hope to unlock the secrets of this elusive substance. One innovative approach to studying dark matter within the web is the use of machine learning and artificial intelligence. These tools have revolutionized the analysis of astronomical data, allowing scientists to identify patterns and correlations that would be impossible to detect manually. For instance, AI algorithms can analyze large-scale surveys to map the distribution of dark matter with unprecedented accuracy, providing new insights into its role in the cosmic web. The cosmic web's filaments also serve as pathways for galaxy migration, a phenomenon that has profound implications for understanding galaxy evolution. As galaxies move along the web's filaments, they interact with their environment, experiencing processes like gas stripping, tidal forces, and mergers. These interactions can trigger star formation, alter galaxy morphology, or even lead to the formation of new structures within the web. By studying these processes, scientists can piece together the complex interplay between galaxies and the larger cosmic environment. In addition to its scientific significance, the cosmic web inspires awe and wonder, inviting us to contemplate the profound interconnectedness of all things. Its delicate balance of order and chaos, simplicity and complexity, serves as a reminder of the beauty and intricacy of the universe. This perspective encourages a sense of unity and humility, fostering a deeper appreciation for the cosmos and our place within it. As we continue to probe the cosmic web's mysteries, new questions inevitably arise. What is the ultimate fate of the web? How does it influence the formation of life in the universe? What does its structure reveal about the fundamental nature of reality? These questions push the boundaries of human knowledge, challenging us to think beyond our immediate experiences and explore the infinite possibilities of the cosmos. The cosmic web is not just a physical structure, it is a symbol of connection and discovery. It represents the human spirit's relentless pursuit of knowledge and the quest to understand our place in the grand tapestry of existence. By studying the web, we not only uncover the secrets of the universe but also deepen our understanding of ourselves and our relationship with the cosmos. As we delve further into the cosmic web, the interconnectedness of the universe becomes even more apparent. It is not just a structure of gas and dark matter, it's a dynamic, evolving organism. Every filament, every void, and every cluster serves as a piece of a much larger puzzle that we are only beginning to understand. One aspect of the cosmic web that has intrigued scientists for years is the role of supermassive black holes in its development and functioning. Supermassive black holes, found at the centers of most galaxies, exert a powerful influence on their environments. They are thought to play a key role in regulating galaxy formation and evolution. In the cosmic web, these black holes are not isolated entities. They interact with their surroundings, affecting the motion of stars, gas, and even entire galaxy clusters. Through processes like the release of high-energy radiation and the accretion of matter, supermassive black holes can alter the behavior of galaxies and the structure of the web itself. This connection between black holes and the cosmic web is fascinating because it suggests a feedback loop. The growth of black holes can influence the formation and dynamics of galaxies, while the gas and material drawn into the web can provide fuel for black hole activity. Some researchers propose that the cosmic web's filaments could serve as highways for the material feeding into black holes, further enhancing their growth and activity. The energy emitted by these black holes could, in turn, regulate the rate of star formation in surrounding galaxies, preventing excessive star formation and keeping the universe in a delicate balance. Another intriguing aspect of the cosmic web is its connection to dark energy and the accelerating expansion of the universe. While we know that dark energy is driving the universe apart at an ever-increasing rate, its effect on the cosmic web is not yet fully understood. Theoretically, dark energy could be stretching the web, causing the filaments to become more elongated and the voids to grow larger. This would have profound implications for the future of the universe. If the cosmic web continues to stretch indefinitely, the distance between galaxy clusters would increase, potentially leading to a scenario where the universe becomes an even more isolated and desolate place. Yet, there is also a counter-theory. Some cosmologists suggest that the cosmic web could eventually experience a contraction due to gravitational forces. If dark energy's influence wanes over time, gravity might regain dominance, causing the cosmic web to collapse in on itself. This would create a dramatic reversal of the universe's current expansion, potentially leading to a big crunch, where all matter and energy are drawn back into a singularity. Whether the cosmic web will continue to expand or contract remains a critical question that hinges on our understanding of dark energy and the ultimate fate of the universe. There is another level of mystery that emerges from the study of the cosmic web: the role of filaments in the formation of life. While the cosmic web is predominantly filled with dark matter, gas, and galaxies, it is possible that some of the chemical ingredients necessary for life could have originated within these filaments. For instance, the filaments are not just lines of gas and dark matter, they also contain trace elements and molecules that could serve as building blocks for life. The web, then, could act as a kind of cosmic conduit, facilitating the exchange of materials across vast distances, potentially helping to spread the raw ingredients for life across the universe. This idea raises intriguing possibilities about the distribution of life. Could life on Earth have originated from material carried along these cosmic highways seeded by the web itself? Could the filaments connect distant star systems, creating pathways for life to travel through the universe? If so, the cosmic web might not only be a structure of galaxies and matter but also a potential highway for life itself, bridging the vast gaps between stars and galaxies, uniting them in ways we have yet to fully comprehend. The idea that the cosmic web could play a role in the spread of life extends to the more speculative realm of Panspermia, the hypothesis that life, or at least the building blocks of life, could be distributed throughout the universe by natural processes. If the cosmic web's filaments could carry material between galaxies, it's conceivable that life could be transported along these cosmic highways, creating the potential for life to exist in distant parts of the universe, far beyond Earth. This concept has profound implications for the search for extraterrestrial life. If life is indeed able to travel along the cosmic web, the search for life may need to extend beyond the boundaries of our own galaxy and look for signs of life in distant clusters of galaxies connected by these intergalactic highways. As we continue to explore the cosmic web, we are constantly confronted with new questions that push the boundaries of our understanding. How do the cosmic filaments interact with each other? What role do they play in the formation and destruction of galaxies? What can we learn from the voids that exist between the filaments? The answers to these questions will undoubtedly reshape our understanding of the universe and our place within it. What makes the cosmic web so fascinating is not just its immense scale but its complexity. The universe is not a random, chaotic place. It is governed by intricate patterns and structures, some of which are just beginning to be uncovered. The cosmic web is the largest known structure in the universe, and it provides a stunning example of how the universe is interconnected. The study of the web is not only about understanding the universe's physical structure but also about exploring the very nature of space, time, and matter. Moreover, the cosmic web serves as a reminder of just how little we know about the universe. Despite all of our advancements in science and technology, we are still grappling with fundamental questions about the universe's origins, its composition, and its fate. The cosmic web is not just a scientific mystery, it is a philosophical one as well. It challenges our notions of space and time, encouraging us to think beyond our immediate experiences and explore the infinite possibilities of the cosmos. In the future, as we continue to develop new technologies and gather more data, we will likely uncover even more secrets hidden within the cosmic web. With advancements in space telescopes, computational models, and particle physics, the potential for discovery is limitless. The cosmic web represents not only the universe's vastness but also the endless possibilities for exploration and understanding. The more we learn about the cosmic web, the more we realize how much we have yet to discover. It is a reminder of the vastness of the universe and our place within it. As we continue to study the cosmic web, we will uncover more about the universe's origins, its structure, and its ultimate fate. And in doing so, we will be taking one step closer to answering the most profound questions about existence itself. As we peer deeper into the cosmos and examine the cosmic web, the role of dark energy in this vast structure becomes even more crucial. While dark matter forms the scaffolding of the web, dark energy is the invisible force that pushes galaxies apart, driving the accelerated expansion of the universe. The interplay between dark matter, dark energy, and the filaments of the cosmic web is still a source of intense research and speculation. How do these forces work together to shape the universe as we see it? Dark energy, which makes up roughly 68% of the universe, is the primary culprit behind the accelerating expansion of space. It exerts a repulsive force, pushing galaxies apart and stretching the fabric of the universe. This is in contrast to the attractive force of gravity, which pulls matter together. The result is a cosmic tug-of-war between these forces, with dark energy driving the expansion and gravity trying to pull matter together. Over time, dark energy has come to dominate this balance, causing the rate of expansion to increase. But what does this mean for the cosmic web? If dark energy continues to stretch the universe, the filaments of the cosmic web could become even more elongated and sparse. The voids between clusters of galaxies could grow larger, leading to an ever-expanding universe that is less dense and more spread out. This would have profound implications for the future of the universe. Some scientists speculate that this could eventually lead to a heat death, where galaxies, stars, and other cosmic objects are so far apart that they can no longer interact, or even be seen from one another. The universe would become a dark, cold expanse, with only the remnants of once energetic stars and galaxies scattered throughout. However, the role of dark energy in the cosmic web is not yet fully understood. While it is clear that dark energy is causing the universe to expand, how it interacts with the matter in the cosmic web is still a subject of much debate. Some theorists suggest that dark energy could be responsible for creating the large-scale structure of the universe, shaping the filaments and voids in ways we are only beginning to understand. Could dark energy be the key to unlocking the mysteries of the cosmic web? In the quest to answer these questions, scientists are developing new tools and technologies to probe the nature of dark energy and its relationship to the cosmic web. For example, upcoming space missions like the James Webb Space Telescope are expected to provide unprecedented views of the universe, allowing us to observe galaxy clusters and their surrounding structures in more detail than ever before. These observations will help us refine our models of the cosmic web and dark energy, shedding light on how these forces work together to shape the universe. In addition to dark energy, the nature of dark matter remains one of the most elusive mysteries in astrophysics. Unlike normal matter, which emits light and interacts with electromagnetic forces, dark matter is invisible and interacts only through gravity. Despite its invisibility, dark matter is believed to make up about 27% of the universe's mass, playing a critical role in the formation of the cosmic web. The gravity of dark matter is responsible for pulling ordinary matter into clumps, forming the galaxy clusters that sit at the nodes of the cosmic web. But dark matter does not just hold galaxies together, it also helps to create the very filaments that connect these clusters. These dark matter filaments form the backbone of the cosmic web, guiding the movement of galaxies and gas throughout the universe. Without dark matter, the structure of the cosmic web would be vastly different. But the true nature of dark matter remains a mystery. Scientists have proposed various theories, including the possibility that dark matter consists of exotic particles that interact very weakly with ordinary matter. If this is the case, detecting dark matter directly would be incredibly challenging. However, indirect evidence from the cosmic web and galaxy motion suggests that dark matter is real and plays a pivotal role in shaping the universe. As we continue to explore the cosmic web and its mysteries, we are also confronted with the question of what lies beyond it. The cosmic web is just one layer of the universe's vast structure. What exists outside the web? Is the cosmic web part of a larger multiverse, a network of parallel universes connected by similar structures? This is one of the most speculative and mind-bending ideas in cosmology, but it is a topic that some researchers are beginning to explore. The multiverse theory proposes that our universe is just one of many universes that exist in a larger, interconnected reality. These universes could be similar to ours, with their own cosmic webs and structures, or they could be entirely different, governed by different physical laws. If the multiverse exists, it could explain some of the fundamental mysteries of the universe, such as the fine-tuning of the constants of nature that allow life to exist. Some scientists suggest that the cosmic web could be a feature of a multiversal network, linking together parallel universes through shared structures and forces. While the multiverse remains a speculative idea, it underscores the fact that the universe is far more complex and mysterious than we can fully comprehend. The cosmic web, with its vast filaments and galaxy clusters, is just one layer of a much deeper, more intricate reality. As we continue to study the web, we may eventually uncover clues that point to the existence of a larger, interconnected multiverse. The answers to these questions will require breakthroughs in both theory and observation, and it is likely that the future of cosmology will be shaped by these exciting, uncharted ideas. In the meantime, the study of the cosmic web continues to provide us with valuable insights into the structure and evolution of the universe. From the role of dark matter and dark energy to the possibility of intergalactic highways connecting distant galaxy clusters, the cosmic web is a source of constant discovery and wonder. Each new observation brings us closer to understanding how the universe is connected and how it has evolved over time. And as we continue to unlock the secrets of this vast structure, we may find that the cosmic web holds the key to understanding some of the most profound mysteries of existence itself. The cosmic web is not just a scientific concept, it is a testament to the grandeur and complexity of the universe. It is a reminder that the universe is far from being a simple, empty space. Instead, it is a dynamic, interconnected system of galaxies, gas, dark matter, and dark energy, all working together to shape the fabric of reality itself. By studying the cosmic web, we are not only learning about the universe's past and present but also uncovering the potential for its future. And in doing so, we are taking part in one of the greatest scientific endeavors of our time. As we continue to explore the cosmic web, we will undoubtedly encounter more mysteries that challenge our understanding of the universe. Whether it is the true nature of dark energy, the role of supermassive black holes, or the possibility of a multiversal network, the cosmic web will remain a focal point of scientific inquiry for years to come. And as we unveil its secrets, we may find that the universe is even more awe-inspiring and interconnected than we ever imagined. As we look deeper into the cosmic web, it's essential to recognize that the web itself is not a static structure. The universe is constantly evolving, with galaxies, gas, and dark matter moving and interacting within the web. The cosmic web isn't simply a snapshot of the universe at one point in time, it is a dynamic and ever-changing system, with new filaments forming, galaxy clusters growing, and voids expanding. This dynamic nature of the cosmic web is driven by several forces that operate over vast timescales. One of the key forces at work is gravity. Over billions of years, gravity causes galaxies to move toward one another, eventually forming clusters. At the same time, the dark matter filaments that make up the cosmic web act as highways, guiding the movement of these galaxies. The gravity of dark matter helps to pull galaxies toward the regions where dark matter density is highest, which results in the formation of galaxy clusters at the nodes of the web. The expansion of the universe also plays a significant role in shaping the cosmic web. As space itself expands, the distances between galaxies increase. This expansion, driven by dark energy, is not uniform across the universe. Some regions are expanding more rapidly than others, leading to the stretching and elongation of the cosmic web's filaments. Over time, the expansion of the universe will continue to stretch the web, causing galaxy clusters to become more distant from each other, and the voids between them to grow larger. This process is happening right now, and its effects can be seen in the large-scale structure of the universe. The future of the cosmic web is intimately tied to the fate of the universe itself. If the current rate of expansion continues, the cosmic web will continue to stretch, and the galaxy clusters that make up the nodes of the web will become increasingly isolated. This could lead to a universe that is more diffuse, with galaxies becoming so distant from one another that they can no longer interact, or even be seen by one another. This scenario is often referred to as the Big Freeze, where the universe continues to expand and cool, eventually reaching a state where all stars burn out, and galaxies drift apart into an eternal darkness. But the fate of the cosmic web and the universe is still uncertain. While current observations suggest that the universe is expanding at an accelerating rate, it is possible that new discoveries could change our understanding of the universe's future. Some theories suggest that the expansion of the universe could eventually slow down or even reverse, leading to a big crunch, where the universe collapses back in on itself. If this were to happen, the cosmic web would be compressed, with galaxies and dark matter filaments being drawn together once again. In addition to gravity and dark energy, there are other factors that influence the evolution of the cosmic web. One such factor is the process of galaxy mergers. As galaxies move through the cosmic web, they sometimes collide and merge with one another. These mergers can lead to the formation of larger galaxies and more massive galaxy clusters. The merging of galaxies can also trigger bursts of star formation and the release of vast amounts of energy, contributing to the evolution of the web's structure. These interactions can change the dynamics of galaxy clusters and alter the distribution of gas and dark matter within the web. The role of supermassive black holes is another intriguing aspect of the cosmic web. At the center of most large galaxies lies a supermassive black hole, whose gravity influences the surrounding environment. These black holes can have a profound impact on the cosmic web. For instance, when a supermassive black hole consumes material from its surroundings, it can release immense amounts of energy, creating powerful jets and winds that can alter the properties of the gas and dark matter in the web. These phenomena can disrupt the formation of new stars and influence the evolution of galaxies. One of the most remarkable aspects of the cosmic web is its sheer scale. The distances between the filaments and galaxy clusters are so vast that they are almost incomprehensible. The universe is so large that light from distant galaxies takes billions of years to reach us. Even the nearest galaxies, located in the local group, are separated by millions of light years. The cosmic web spans billions of light years, making it one of the largest structures in the universe. Despite its immense size, the web is not uniform. It is made up of dense regions, like galaxy clusters, and vast voids where very few galaxies exist. This uneven distribution of matter gives the cosmic web its characteristic filamentary structure. The study of the cosmic web and the forces that shape it has led to some groundbreaking discoveries. One of the most significant discoveries in recent years has been the identification of the so-called cosmic voids. These voids are vast, empty regions of space that make up most of the volume of the universe. They are the opposite of galaxy clusters and filaments, and their discovery has provided important insights into the large-scale structure of the universe. The cosmic web is also a powerful tool for studying the properties of dark matter. Because dark matter interacts only through gravity, it cannot be directly observed. However, by studying the distribution of galaxies and gas within the cosmic web, scientists can infer the presence of dark matter and map its distribution. The filaments of the cosmic web, where dark matter is most concentrated, act as a cosmic map that can help us understand the distribution and properties of dark matter in the universe. The cosmic web also plays a key role in the formation and evolution of galaxies. It is believed that galaxies form within the dense regions of the cosmic web, where the gravitational pull of dark matter filaments causes gas and dust to collapse, leading to the birth of stars and galaxies. The interactions between galaxies within the web can lead to galaxy mergers, star formation, and other processes that shape the galaxies over time. In recent years, astronomers have developed new techniques and technologies to study the cosmic web in more detail. The advent of advanced telescopes, such as the James Webb Space Telescope, has allowed scientists to peer deeper into the universe than ever before. These observations are helping to refine our understanding of the cosmic web and its role in the larger structure of the universe. The study of the cosmic web is not just about understanding the universe's past and present, it is also about predicting its future. As we learn more about the forces that shape the web, we can make more accurate predictions about the future evolution of the universe. Will the cosmic web continue to expand, or will it eventually collapse? What will happen to the galaxies within the web? These are questions that will shape the future of cosmology and our understanding of the universe. The cosmic web is one of the most fascinating and complex structures in the universe. It is a vast network of galaxy clusters, filaments, and voids shaped by the forces of gravity, dark matter, and dark energy. It connects the galaxies of the universe, forming a vast, interconnected system that spans billions of light years. The study of the cosmic web has already led to groundbreaking discoveries, and as our understanding of dark matter, dark energy, and the universe itself continues to evolve, the cosmic web will undoubtedly reveal even more of its secrets. The mysteries of the cosmic web are far from being solved, but each new discovery brings us closer to understanding the universe in all its complexity. And as we continue to explore the vast expanse of space, we will undoubtedly uncover even more astonishing and mind-bending truths about the cosmic web and the universe itself. The journey of discovery has only just begun. As we continue our exploration of the cosmic web, one of the most profound aspects of this structure is how it challenges our understanding of the universe and the fundamental forces that govern it. It is not just a mere collection of galaxies, gas, and dark matter, it is a testament to the complexity and interconnectedness of the cosmos, revealing the intricate dance between gravity, dark matter, and dark energy. These interactions are constantly shaping the universe in ways we are only beginning to comprehend. One of the most striking features of the cosmic web is its fractal-like structure. The web is composed of filaments, voids, and clusters that seem to repeat themselves at different scales, from the largest galaxy clusters to the smallest individual galaxies. This fractal nature suggests that the universe has a self-similar structure, where the same patterns can be found at different levels of magnification. This is a concept that challenges traditional views of the universe as being random or chaotic. Instead, the cosmic web offers a glimpse into a universe that is governed by underlying order and structure. The filaments that make up the cosmic web are not just composed of visible matter, but also dark matter, which makes up a significant portion of the mass in the universe. Dark matter, though invisible to our instruments, exerts a gravitational pull that influences the movement of galaxies and gas within the web. The exact nature of dark matter is still unknown, but its presence is essential to understanding the formation and behavior of the cosmic web. Without dark matter, the gravitational forces required to hold the filaments of the web together would not be strong enough, and the structure of the web would collapse. In recent years, scientists have made significant strides in understanding the role of dark matter in the cosmic web. One of the most exciting developments is the discovery of the dark matter halos that surround galaxies and galaxy clusters. These halos are vast regions of dark matter that extend far beyond the visible boundaries of galaxies. They provide the gravitational foundation for the cosmic web, allowing galaxies to form and move along the filaments. These dark matter halos are invisible to conventional telescopes, but their existence has been inferred through their gravitational effects on surrounding galaxies and gas. The presence of dark matter is not the only mystery associated with the cosmic web. Another intriguing aspect is the role of dark energy in shaping the large-scale structure of the universe. Dark energy is the mysterious force that is causing the accelerated expansion of the universe. Its influence is felt most strongly in the vast voids between galaxy clusters, where its repulsive force counteracts the pull of gravity. As a result, the cosmic web is not a static structure, but a dynamic system that is constantly evolving as the universe itself expands. The interplay between dark matter and dark energy is one of the most critical factors in understanding the future of the cosmic web and the universe as a whole. One of the most exciting aspects of studying the cosmic web is the potential for new discoveries that could revolutionize our understanding of the universe. The upcoming advancements in astronomical technology, such as the launch of the James Webb Space Telescope, will provide unprecedented insights into the structure and evolution of the cosmic web. With its advanced infrared capabilities, the James Webb Space Telescope will be able to observe galaxies and filaments that are too distant and faint for current telescopes to detect. This will allow scientists to study the early stages of the cosmic web's formation and perhaps even observe the first galaxies and filaments that emerged after the Big Bang. The study of the cosmic web is also providing valuable insights into the process of galaxy formation. Galaxies do not form in isolation. Rather, they are influenced by the surrounding environment, particularly the gas and dark matter in the cosmic web. As galaxies move through the web, they encounter regions of higher density, where the gravitational pull of dark matter and gas can trigger the collapse of gas clouds, leading to the formation of new stars and galaxies. These interactions between galaxies and their environment play a crucial role in the evolution of galaxies and the structure of the web itself. One of the most intriguing questions that remains unanswered is how the cosmic web will continue to evolve over time. The expansion of the universe, driven by dark energy, is causing the web to stretch, with galaxies moving farther apart from each other. This process is likely to continue for billions of years, leading to a universe that is increasingly diffuse and isolated. However, the ultimate fate of the cosmic web depends on the precise nature of dark energy, and whether its repulsive force will continue to accelerate the expansion of the universe indefinitely. Some theories suggest that the cosmic web will eventually break apart as galaxies move too far away from one another to interact. In this scenario, the cosmic web would become a collection of isolated galaxy clusters, separated by vast, empty voids. Other theories propose that the expansion of the universe could eventually slow down, and gravity could take over, causing the cosmic web to collapse back in on itself. This would result in a big crunch, where all the galaxies, gas, and dark matter would be pulled back together, possibly leading to a new phase of cosmic evolution. Despite the uncertainty surrounding the future of the cosmic web, one thing is clear: the study of this vast, interconnected structure is essential for understanding the universe and its evolution. The cosmic web is not just a collection of galaxies and gas, it is the skeleton of the universe, providing the framework around which all the other structures, stars, planets, and life, are built. Understanding how the web formed, how it has evolved, and how it will continue to evolve is crucial for answering some of the most profound questions in cosmology. As we delve deeper into the mysteries of the cosmic web, we are not just uncovering the secrets of the universe's past and present, we are also gaining insight into its future. The more we learn about the web, the better equipped we will be to understand the ultimate fate of the universe itself. Will the web continue to expand, or will it eventually collapse? Will dark energy continue to drive the accelerated expansion of the universe, or will its influence diminish over time? These questions remain unanswered, but each new discovery brings us one step closer to understanding the vast, intricate network that connects everything in the universe. The cosmic web is a reminder of how much we still have to learn about the universe. It is a structure that spans billions of light years and is composed of matter that we can't yet fully understand. But as we continue to study it, we uncover more and more of the cosmic tapestry that stretches out before us, offering a glimpse into the deeper workings of the universe and our place within it. The journey of discovery is far from over, and the cosmic web is just one of many mysteries waiting to be unraveled. As we continue to probe the vast expanse of the cosmic web, it's crucial to understand how its structure and behavior influence everything within the universe. The filamentous threads that stretch across space, linking galaxy clusters, are not mere abstract concepts. They represent a vast, intricate network of material and forces that dictates the evolution of galaxies, stars, and even life itself. One fascinating aspect of the cosmic web is the distribution of galaxies along these filaments. Rather than being scattered randomly throughout the universe, galaxies tend to align along the strands of this web. They clump together into dense clusters where the filaments intersect, forming some of the largest structures in the cosmos. The areas between the filaments, known as voids, are relatively empty, containing very few galaxies. These voids may appear as gaps in the universe, but they are just as important as the filaments and clusters in shaping the large-scale structure of the cosmos. The galaxies' positions along the filaments are far from coincidental. They are the result of complex gravitational forces at play, exerted by dark matter and gas, which dictate how galaxies form, evolve, and interact with each other over cosmic time scales. The cosmic web's filaments aren't just channels that galaxies travel through. They are also active environments for the creation of new galaxies and stars. As galaxies move through these filaments, they encounter various types of gas, including warm gas, hot gas, and cold molecular gas. In these regions, gas clouds can become dense enough to collapse under their own gravity, leading to the formation of new stars. In fact, a significant amount of star formation takes place in the cosmic web, specifically in the regions surrounding galaxy clusters. This process, known as starburst activity, is triggered when galaxies collide or pass through dense regions of the web, compressing the gas and igniting the birth of stars at a rapid rate. These star-forming regions within the filaments give rise to new generations of stars and contribute to the overall chemical enrichment of the universe. The role of gas in the cosmic web is not limited to star formation. It also acts as a conduit for the transfer of energy across vast distances. The gas within the web is often heated to extreme temperatures by shocks and gravitational interactions. These energetic events can trigger the release of massive amounts of radiation, which in turn heats the surrounding gas. This process is critical for understanding the evolution of galaxies and clusters, as it affects the cooling rates of gas and the balance between heating and cooling in the cosmic web. As we peer deeper into these structures, we uncover the delicate interplay between matter and energy that shapes the universe on both large and small scales. Dark matter, as we have already discussed, plays an integral role in the formation and maintenance of the cosmic web. It is the invisible scaffold upon which the visible structure of the web is built. The gravitational influence of dark matter dictates the motion of galaxies and the distribution of gas along the filaments. It is believed that the cosmic web's largest and most massive structures are held together by the gravitational pull of dark matter, which ensures that the filaments remain intact. Without dark matter, the gravitational forces necessary to hold these vast structures together would be absent, and the web would unravel. Despite its crucial role, dark matter remains one of the greatest mysteries of modern physics. We know it exists because of its gravitational effects on visible matter, such as galaxies and galaxy clusters, but we have yet to detect it directly. The search for dark matter is one of the most exciting areas of research in cosmology and particle physics. Scientists have proposed several candidates for dark matter, including weakly interacting massive particles, WIMPs, and axions, but none of these have been definitively observed. Understanding dark matter is essential for unlocking the full nature of the cosmic web, as it provides the missing mass and energy that influence the behavior of galaxies and other structures. Meanwhile, dark energy, which is driving the accelerated expansion of the universe, plays a different but equally important role in shaping the cosmic web. While dark matter's gravitational pull helps to pull galaxies together, dark energy acts as a counterforce, causing galaxies to move apart. The expansion of the universe, fueled by dark energy, is continuously stretching the cosmic web, making it more diffuse over time. This expansion means that the distances between galaxy clusters are growing, and the filaments are being stretched thinner and thinner. The effect of dark energy on the cosmic web is still an active area of research, as scientists seek to understand how it influences the behavior of the universe on the largest scales. Some theories suggest that dark energy's influence will eventually cause the cosmic web to disassemble, leading to a future where galaxies are isolated and far apart. The way the cosmic web is structured and how it evolves over time has profound implications for the fate of the universe. If dark energy continues to dominate, the universe will keep expanding at an accelerated rate. As the filaments stretch, the gravitational bonds between galaxy clusters will weaken, and the cosmic web may become increasingly fragmented. In this scenario, galaxies would drift farther and farther from each other, and the clusters would become more isolated. Eventually, all the individual galaxy clusters could become separated, leaving behind a vast, empty expanse of space. Alternatively, if the influence of dark energy were to diminish, the expansion of the universe could slow down. In this case, gravity would take over, and the cosmic web could begin to collapse in on itself. This scenario, known as the Big Crunch, would result in a dramatic restructuring of the universe. All the galaxies, stars, and dark matter would be drawn back together, possibly culminating in a singularity, where all matter and energy are compressed into an infinitely small point. The Big Crunch would mark the end of the current phase of the universe, potentially leading to a new cycle of creation and destruction. However, the ultimate fate of the cosmic web is still uncertain. The expansion of the universe, the influence of dark energy, and the behavior of dark matter are all factors that remain incompletely understood. The discovery of new phenomena or the detection of unknown forces could dramatically alter our understanding of the cosmic web's future. As we continue to study the universe, we inch closer to answering these profound questions, but the true nature of the cosmos may remain elusive for generations to come. One exciting development in our exploration of the cosmic web is the role that upcoming technologies will play in unlocking its secrets. The James Webb Space Telescope, scheduled for launch in the near future, will allow us to observe distant galaxies and filaments in unprecedented detail. With its advanced infrared capabilities, it will provide a clearer view of the early stages of the cosmic web's formation, allowing scientists to study how galaxies, gas, and dark matter came together in the aftermath of the Big Bang. This telescope could offer groundbreaking insights into the nature of dark matter, the formation of the cosmic web, and the role of dark energy in shaping the universe. Additionally, advancements in radio astronomy are also opening up new possibilities for observing the cosmic web. Radio telescopes, such as the Square Kilometre Array (SKA), are poised to revolutionize our understanding of the web by allowing us to map the distribution of hydrogen gas, the most abundant element in the universe, across vast distances. This will give scientists a more complete picture of the web's structure and the role of gas in its evolution. The SKA, along with other next-generation observatories, will provide critical data that will help refine our models of the cosmic web and expand our understanding of the universe. As our technological capabilities grow, so too will our ability to observe and comprehend the cosmic web. We stand on the precipice of a new era in astronomy, one where we may finally begin to unravel the mysteries of the vast, interconnected structure that stretches across the universe. In the coming years, we may learn more about the forces and processes that shape the cosmic web than ever before, and these discoveries will undoubtedly lead to even more questions. The universe is full of mysteries, and the cosmic web remains one of the most enigmatic and awe-inspiring of them all. As we peer further into the cosmic web, one of the most profound mysteries lies in understanding the intricate dynamics of these filaments. Beyond the simple notion that galaxies are clustered together in vast structures, there is an entire dance of gravitational forces, dark matter, and gas that plays out across the universe. The cosmic web is not static. It is a dynamic, ever-evolving structure, and its evolution is driven by forces that operate on scales so vast and so subtle that they are often invisible to us. One of the key drivers of this evolution is the complex interaction between galaxies and their surrounding environment. As galaxies move through the cosmic web, they are not isolated objects. They are constantly influenced by the gravitational pull of nearby galaxies, gas clouds, and dark matter. This interaction leads to a variety of phenomena, including galaxy mergers, tidal forces, and the accretion of gas into galaxy clusters. These processes shape the formation and behavior of galaxies, leading to the creation of massive, intricate systems of stars, gas, and dark matter. When galaxies collide or pass close to each other, their gravitational forces can cause dramatic effects. In some cases, these interactions can result in the merging of galaxies, a process that can trigger intense bursts of star formation. These starbursts occur when gas clouds are compressed by the gravitational forces of the colliding galaxies, causing the gas to collapse and ignite new stars at a rapid rate. The formation of new stars is just one of the many consequences of galaxy interactions. As galaxies merge, their gas and dark matter also mix, reshaping the structure of the galaxies and their surrounding environment. These interactions can also have long-term effects on the cosmic web itself. As galaxies merge and interact, they can alter the distribution of matter in the web, causing the filaments to stretch and warp in response to these changes. In some cases, these interactions may even lead to the creation of new filaments, or the disruption of existing ones. This constant reshaping of the cosmic web is an ongoing process that will continue for billions of years, as galaxies continue to move, collide, and merge in the vast reaches of space. At the same time, the influence of dark matter remains an essential factor in shaping the cosmic web. Although dark matter cannot be directly observed, its presence is inferred from its gravitational effects on visible matter. Dark matter forms the invisible scaffolding upon which the visible structures of the universe are built, including the filaments of the cosmic web. The gravitational pull of dark matter is what keeps galaxies and galaxy clusters bound together, even in the face of the expansion of the universe. As we have mentioned before, dark matter plays a pivotal role in maintaining the integrity of the cosmic web. Without the gravitational influence of dark matter, the filaments would not hold together, and the large-scale structure of the universe would be drastically different. However, the true nature of dark matter remains one of the most elusive mysteries of modern physics. While its existence has been confirmed through its gravitational effects, scientists have yet to identify what dark matter is made of. Theories abound, ranging from weakly interacting massive particles, WIMPs, to axions, but so far, no direct evidence has been found. In addition to dark matter, the role of gas within the cosmic web cannot be overstated. The web is primarily composed of hot, diffuse gas that fills the voids between galaxies and galaxy clusters. This gas is often referred to as the cosmic web gas, or the intergalactic medium, IgM. The IgM is made up of mostly hydrogen, with trace amounts of helium and other elements. This gas is not uniformly distributed throughout space. Rather, it is concentrated along the filaments of the cosmic web, where it serves as a medium for the transfer of energy and matter between galaxies and clusters. The IgM plays a critical role in the evolution of the cosmic web. As galaxies move through these gas-rich regions, they can exchange material with the IgM, adding or removing gas from their own reservoirs. This exchange of material can influence the rate of star formation in galaxies, as well as the overall evolution of the galaxy itself. Additionally, the gas within the IgM is often heated to extremely high temperatures by shocks and other energetic processes. This heating can affect the cooling rates of gas in galaxies and clusters, influencing their ability to form new stars. The IgM is also responsible for the transmission of radiation across vast distances. The gas within the cosmic web absorbs and re-emits radiation from galaxies, stars, and other sources, creating a complex network of light that illuminates the entire universe. This radiation is often in the form of ultraviolet and X-ray light, which can travel through the gas and reveal important information about the conditions in the cosmic web. By studying the way radiation interacts with the IgM, scientists can gain insights into the physical properties of the web, including its temperature, density, and composition. In recent years, scientists have made significant strides in understanding the properties of the intergalactic medium. Observations made with advanced telescopes, such as the Hubble Space Telescope and the Chandra X-ray Observatory, have provided detailed images and data on the structure and behavior of the IgM. These observations have revealed that the gas in the cosmic web is not uniform but rather forms a complex, filamentous structure that mirrors the distribution of galaxies and galaxy clusters. The filaments of the cosmic web act as highways for the flow of gas, dark matter, and energy across the universe, connecting galaxy clusters in a vast, interconnected network. As we study the cosmic web in greater detail, we are beginning to uncover new and exciting discoveries about the universe's most distant and mysterious regions. The cosmic web, with its intricate filaments of gas and dark matter, holds the key to understanding the large-scale structure of the universe and its evolution over time. By continuing to observe and study this massive web, we hope to gain a deeper understanding of the forces and processes that govern the universe. From the formation of galaxies and stars to the mysterious nature of dark matter and dark energy, the cosmic web offers a fascinating glimpse into the intricate workings of the universe. One of the most exciting aspects of studying the cosmic web is that it holds the potential to answer some of the most profound questions in cosmology. How did the universe form and evolve? What is the true nature of dark matter and dark energy? How do galaxies and stars form and interact with one another? These are questions that have puzzled scientists for centuries, and the cosmic web may provide the answers. The future of cosmic web research looks incredibly promising. With the advent of new telescopes and observational techniques, we are on the verge of uncovering even more details about the structure and behavior of the cosmic web. The James Webb Space Telescope, for example, will provide unprecedented views of distant galaxies and their surroundings, allowing scientists to study the early stages of the cosmic web's formation. Similarly, advancements in radio astronomy, such as the Square Kilometre Array, SKA, will allow us to map the distribution of gas and dark matter across vast distances, providing a more detailed picture of the web's structure. As we continue to explore the cosmic web, we may uncover new phenomena that challenge our current understanding of the universe. The discoveries made over the next few decades will likely revolutionize our understanding of cosmology and lead to a deeper appreciation of the vast, interconnected structure that binds the universe together. The cosmic web is not just a fascinating feature of the universe. It is a crucial piece of the puzzle that will help us unlock the mysteries of the cosmos. As we venture deeper into the mysteries of the cosmic web, it's important to recognize that the cosmic highways of gas and dark matter are not merely passive structures. They are actively shaping the future of the universe. These intergalactic highways are conduits of matter, energy, and information that facilitate the growth and interaction of galaxies across vast expanses of space. By studying these highways, we unlock the potential to understand the fundamental processes that govern the universe, from the formation of galaxies to the larger cosmological forces that define the very fabric of reality. In a sense, these filaments act as the veins of the cosmic organism, channeling energy between clusters of galaxies, feeding them, and allowing for the interaction of countless cosmic entities. However, the impact of these cosmic highways goes beyond just structural organization. The dynamic interactions within the cosmic web could have far-reaching consequences, particularly when it comes to the future of the universe itself. In this vast network, gas is not simply an inert substance but is constantly moving and interacting. The process of accretion, the pulling in of gas from surrounding regions, plays a critical role in the growth of galaxy clusters. The movement of gas through these filaments contributes to the formation of the galaxy clusters themselves, creating dense regions where galaxies congregate. The inflow of gas into these clusters is also responsible for sustaining the activity of supermassive black holes. As gas is pulled into these black holes, it is heated to extreme temperatures, releasing powerful jets of energy that can influence the surrounding region. This process, known as active galactic nucleus (AGN) activity, can have profound effects on the evolution of galaxies and clusters in the cosmic web. In addition to the matter that is pulled into these massive structures, the gas within the cosmic web is constantly being affected by other energetic processes, such as shocks and cosmic radiation. These processes can heat up the gas, transforming it into a hot, ionized state. This heated gas can then flow through the cosmic filaments, spreading energy across vast distances and influencing the surrounding galaxies. In some cases, the shockwaves generated by these processes can trigger the formation of new stars, causing bursts of star formation that further enrich the cosmic web. The interplay between gas, radiation, and dark matter within these filaments creates a feedback loop that drives the continuous evolution of the cosmic web. What's more, these cosmic highways are not static. As we've mentioned, they're subject to a variety of forces that can cause them to stretch, warp, or break apart over time. As galaxies and galaxy clusters interact, the structure of the cosmic web is continuously reshaped, with new filaments being created while older ones may be destroyed or altered beyond recognition. This process of transformation is not limited to any particular region of the universe but is instead a universal feature of the cosmic web. It's a constant cycle of creation and destruction, where new structures emerge, interact, and then evolve into something completely new. The dynamic nature of the cosmic web raises fascinating questions about the future of the universe. Will the cosmic web continue to stretch and evolve, eventually leading to the collapse of galaxy clusters and the end of the universe as we know it? Or will the expansion of the universe cause the filaments to stretch to the point where they dissolve, leaving behind a more diffuse and less structured universe? These questions are far from easy to answer, but the study of the cosmic web provides us with the tools and insights needed to better understand the potential futures of the universe. Moreover, the cosmic highways are not just a local phenomenon. They span across enormous distances, connecting galaxy clusters and far-flung corners of the universe. These highways transcend the boundaries of individual galaxies and clusters, creating a vast, interconnected web that links the entire universe together. The sheer scale of this network is almost incomprehensible. The distance between galaxy clusters can range from tens of millions to hundreds of millions of light-years, yet these filaments bridge the gaps between them, providing a continuous, interconnected flow of matter and energy. The cosmic web may also hold the key to some of the most profound mysteries in cosmology, particularly when it comes to the nature of dark matter and dark energy. These enigmatic substances make up the majority of the universe's mass and energy, yet their properties remain largely unknown. The filaments of the cosmic web are composed primarily of dark matter, which does not emit or interact with light, making it invisible to traditional telescopes. However, scientists can observe the effects of dark matter by studying its gravitational influence on visible matter, such as galaxies and gas. The cosmic web provides a natural laboratory for studying dark matter and its role in the structure and evolution of the universe. Dark matter is thought to play a crucial role in the formation of galaxy clusters and the overall structure of the cosmic web. Its gravitational pull is what binds galaxies together within clusters and helps to form the large-scale structure of the universe. Without dark matter, the galaxies within these clusters would fly apart due to the expansion of the universe. The presence of dark matter helps to stabilize the cosmic web, ensuring that galaxies and galaxy clusters remain bound together over billions of years. But dark matter is not the only mysterious substance at play. Dark energy, the force responsible for the accelerated expansion of the universe, also plays a role in the evolution of the cosmic web. While dark energy is not directly linked to the formation of galaxies or clusters, its influence on the expansion of the universe affects the large-scale structure of the cosmic web. As the universe continues to expand, the filaments of the cosmic web are stretched, and the distances between galaxy clusters increase. This stretching of the web could have significant implications for the future of the universe, leading to the eventual dissolution of the cosmic web and the separation of galaxies into isolated regions. In recent years, scientists have made tremendous strides in mapping the cosmic web and studying its structure. Using advanced telescopes and observational techniques, astronomers have been able to identify the locations of galaxy clusters and the filaments that connect them. These observations have provided a wealth of information about the distribution of matter and energy across the universe. Through these observations, scientists have learned that the cosmic web is not uniform, but rather contains vast voids, regions of space that are nearly empty of galaxies and gas, separated by dense filaments that stretch across the universe. The voids themselves are not truly empty but contain sparse gas and dark matter, which are responsible for the gravitational forces that shape the web. By studying the cosmic web in greater detail, scientists are uncovering new and exciting information about the large-scale structure of the universe. The ongoing development of next-generation telescopes and observatories, such as the James Webb Space Telescope, will provide even more detailed views of the cosmic web, allowing scientists to study the formation of galaxies and clusters in unprecedented detail. These advancements will enable scientists to answer some of the most profound questions about the universe's past, present, and future. But the cosmic web is not just a phenomenon of the present or the future. It is a snapshot of the universe's history. The web itself is a record of the universe's evolution, from the early moments after the Big Bang to the present day. By studying the cosmic web, scientists can trace the history of galaxy formation and the growth of large-scale structures over billions of years. The filaments that connect galaxy clusters are remnants of the early universe, shaped by the gravitational pull of dark matter and the interactions between galaxies and gas. As we continue to unravel the mysteries of the cosmic web, we gain a deeper understanding of the universe's past and its potential future. The web provides a window into the forces that have shaped the universe and continue to influence its evolution. From the formation of galaxies and clusters to the mysterious forces of dark matter and dark energy, the cosmic web offers a unique perspective on the fundamental processes that drive the cosmos. The cosmic web is not only a structural feature of the universe but also a dynamic system that evolves over time. As galaxies move and interact within the web, they can trigger profound changes in the surrounding filaments. The formation of superclusters, the largest known structures in the universe, is one such example of this dynamic nature. These superclusters are vast, interconnected regions that contain hundreds or even thousands of galaxies. Superclusters are often formed at the intersections of multiple filaments, where the gravitational forces from nearby galaxy clusters and dark matter filaments cause a concentration of galaxies and gas. However, the process of galaxy cluster formation is not entirely smooth. Sometimes, filaments can become twisted, stretched, or fragmented due to gravitational interactions between galaxies, leading to the formation of new structures. These dynamic processes can cause entire regions of the cosmic web to shift, with galaxies and dark matter being redistributed across vast distances. This type of movement is not just a random process, but rather the result of the delicate balance between gravitational forces, dark energy, and the matter within the web itself. Interestingly, the cosmic web appears to evolve in different ways depending on the scale at which it is observed. On the largest scales, the web structure is primarily determined by the distribution of dark matter and the expansion of the universe. This large-scale structure shapes the formation of galaxy clusters and the overall shape of the web. On smaller scales, however, the evolution of the web is influenced more by the interactions between individual galaxies and the gas within the filaments. These smaller-scale processes include the movement of gas, star formation, and the merging of galaxies, all of which contribute to the growth and transformation of the cosmic web. One of the most intriguing aspects of the cosmic web is the role it plays in galaxy evolution. The filaments that connect galaxy clusters are more than just highways for gas and dark matter. They also influence the growth and development of the galaxies themselves. The gas within these filaments is often a vital source of fuel for galaxies, providing the raw materials for star formation. As galaxies move along the cosmic highways, they encounter other galaxies and experience gravitational interactions that can trigger the formation of new stars, the accretion of gas, and even the merging of entire galaxies. This ongoing process of galaxy evolution has profound implications for our understanding of how galaxies form and grow over time. In the early universe, the cosmic web was much less developed than it is today. However, as galaxies and galaxy clusters formed, the web became more complex, with larger and more intricate structures emerging over billions of years. The ongoing evolution of the cosmic web continues to shape the distribution of galaxies, star clusters, and other cosmic objects, as new filaments form, merge, and break apart. In addition to influencing galaxy formation, the cosmic web also plays a critical role in the evolution of large-scale structures like galaxy clusters and superclusters. As galaxies and dark matter move through the web, they accumulate in certain regions, creating dense clusters of galaxies surrounded by vast voids. These voids are not empty, as we've seen, but rather contain sparse gas and dark matter, which helps to maintain the overall structure of the web. The interaction between these voids and the denser filaments of the web is an essential part of the cosmic dance that drives the evolution of the universe. For a long time, astronomers and cosmologists have relied on theoretical models and computer simulations to study the cosmic web. These models attempt to simulate the behavior of galaxies, dark matter, and gas across vast distances of space, providing valuable insights into the underlying forces at play. While these simulations have provided a great deal of information about the cosmic web's large-scale structure, they have also revealed some surprising results. For example, simulations have shown that the formation of the cosmic web is not a smooth or predictable process. Rather, it is the result of complex interactions between dark matter, gas, and gravity. In some regions of the universe, filaments of dark matter and gas collide or merge, creating regions of intense activity where new galaxies and clusters are born. These regions are often the site of starburst galaxies, where rapid star formation occurs as a result of the intense gravitational forces within the filaments. The collision of gas and dark matter in these regions can also lead to the formation of black holes and other exotic cosmic objects, adding another layer of complexity to the web. The results from simulations and observations also suggest that the cosmic web is not a static structure, but rather a dynamic and ever-evolving system. As galaxies and dark matter interact within the filaments, they can trigger a variety of processes that lead to the formation of new structures, including galaxy mergers, superclusters, and the growth of black holes. In fact, the cosmic web itself may eventually be responsible for the eventual fate of the universe. As we consider the possible futures of the cosmic web, one scenario stands out as particularly intriguing: the possibility of a Big Rip. This theory suggests that the ongoing expansion of the universe could eventually lead to the tearing apart of the cosmic web itself. As dark energy accelerates the expansion of the universe, the filaments that connect galaxy clusters could be stretched beyond their breaking point. In this scenario, the vast network of cosmic highways could collapse, and galaxies, stars, and even the atoms themselves could be ripped apart. While the Big Rip is still a theoretical concept, it is based on our current understanding of dark energy and the expansion of the universe. If the acceleration of the universe continues indefinitely, it is possible that the forces of dark energy will overcome the gravitational forces that hold galaxies and clusters together. In this case, the cosmic web would dissolve, leaving behind a universe of isolated galaxies, drifting farther apart as the fabric of space itself continues to stretch. Alternatively, the cosmic web could continue to evolve and expand for billions of years, potentially leading to the creation of new structures and regions of intense activity. As galaxies and clusters interact, new filaments may form, and the web could become even more complex and interconnected over time. The future of the cosmic web is, like much of cosmology, shrouded in mystery, but what is clear is that it plays a central role in the ongoing evolution of the universe. Through the study of the cosmic web, we gain not only insights into the past and present of the universe but also into its future. The intricate structures of dark matter and gas that make up the web are constantly changing, and their interactions shape the development of galaxies, star systems, and entire galaxy clusters. As our observational tools continue to improve, we will be able to probe deeper into these cosmic highways, revealing more about the fundamental forces that drive the universe's evolution. Ultimately, the cosmic web serves as a reminder of the vastness and complexity of the universe. It's not just a collection of galaxies, but a living, breathing network that connects every corner of the universe in a way that we are only beginning to comprehend. With each discovery, we move closer to understanding how these cosmic highways function, how they have shaped the universe, and how they may continue to evolve in the distant future. The cosmic web, with its vast networks of dark matter and gas filaments, remains one of the most mysterious and awe-inspiring features of the universe. Its scale and complexity stretch beyond the limits of human comprehension, yet its influence on the evolution of the cosmos is undeniable. Every aspect of the cosmic web, from the quiet stretches of voids between galaxy clusters to the intense activity at the intersections of these filaments, affects the behavior of galaxies, stars, and even the fundamental properties of space itself. One of the intriguing elements of the cosmic web is the role of dark matter. While we cannot directly observe dark matter, its presence can be inferred from its gravitational effects on visible matter. Dark matter is thought to be the primary force shaping the structure of the cosmic web. The filaments of the web are composed largely of this mysterious substance, which interacts with visible matter in ways that create the enormous scaffolding of galaxies, galaxy clusters, and voids. In the denser regions of the web, where filaments intersect, dark matter forms the backbone of large structures like superclusters, helping to bind galaxies together. The role of dark matter is not limited to shaping the structure of the web. It also influences the movement of galaxies within the web. The gravitational pull of dark matter causes galaxies to move along specific pathways, following the filaments that connect them to other galaxies or galaxy clusters. In some cases, entire groups of galaxies can move toward each other along these cosmic highways, eventually colliding and merging into new, larger structures. These collisions are not chaotic, but rather the result of gravitational forces pulling galaxies along the filaments, guiding their interactions in a predictable, albeit complex, manner. Gas also plays a critical role in the cosmic web. While dark matter forms the structural framework, gas provides the fuel for star formation and the growth of galaxies. As gas flows along the filaments of the cosmic web, it cools and condenses, leading to the formation of new stars. The gas can also accumulate in galaxy clusters, creating a hot, dense environment where galaxies interact, merge, and evolve. In some cases, the accumulation of gas can trigger a burst of star formation, leading to the creation of starburst galaxies, galaxies that experience rapid and intense star formation. These starburst events are often linked to the gravitational interactions between galaxies as they move along the cosmic highways. Beyond the influence of gas and dark matter, the cosmic web is also shaped by the expansion of the universe. The expansion of space itself causes the filaments of the cosmic web to stretch over time, pushing galaxy clusters farther apart. This expansion has a profound effect on the overall structure of the web, influencing the growth of voids and the formation of new filaments. The acceleration of the universe's expansion, driven by dark energy, could lead to dramatic changes in the future of the cosmic web. Over billions of years, the increasing rate of expansion may cause galaxies to move farther apart, eventually breaking apart clusters and disconnecting the once interwoven filaments. The concept of dark energy adds an additional layer of complexity to the evolution of the cosmic web. Dark energy is the mysterious force responsible for the accelerated expansion of the universe. Its effects are not yet fully understood, but its influence on the cosmic web is becoming more apparent as we gather more data. In regions of the web where dark energy is most prominent, the filaments of dark matter and gas may begin to stretch more rapidly, causing the web to fragment. While this might lead to the eventual dispersal of galaxies and clusters, it also opens the door to new possibilities for the structure of the universe in the distant future. In the far future, the cosmic web may no longer be the interconnected network of galaxies and dark matter filaments that we observe today. As dark energy continues to accelerate the expansion of the universe, galaxies may be carried farther apart, and the dense clusters of galaxies may break up, leaving behind vast, empty voids. This scenario, known as the Big Rip, suggests that the cosmic web could ultimately disassemble, its components stretched beyond recognition. While this idea remains speculative, it underscores the dynamic and ever-changing nature of the universe and the cosmic web's role in its ongoing evolution. However, this is just one possible scenario. The future of the cosmic web is still uncertain, and other outcomes are possible. For example, the gravitational interactions between galaxies and dark matter could eventually lead to the formation of new structures and filaments. In this scenario, the cosmic web would continue to evolve, with new clusters and filaments forming and connecting in ever more intricate patterns. While the idea of a Big Rip is a fascinating concept, it is not the only possible outcome for the cosmic web. The interplay of gravitational forces, dark energy, and the movement of galaxies will continue to shape the universe in ways that we can only begin to imagine. The study of the cosmic web is still in its early stages, and much remains to be learned about this intricate and vast structure. As observational technology advances, astronomers are able to peer deeper into the universe, uncovering more about the web and the forces that shape it. Tools like the Hubble Space Telescope, the James Webb Space Telescope, and future observatories will allow scientists to map the cosmic web with greater precision, revealing more details about the filaments of dark matter and gas that connect galaxy clusters across vast distances. These observations will provide new insights into the nature of dark matter, dark energy, and the overall evolution of the universe. By studying the way galaxies and dark matter move along the cosmic highways, scientists can gain a better understanding of how galaxies form, how they interact, and how the universe itself is evolving. With each new discovery, the cosmic web becomes a little less mysterious, and our understanding of the universe as a whole grows. In the future, the study of the cosmic web could also reveal more about the fundamental forces that govern the behavior of matter and energy on the largest scales. As we uncover more about the intricate connections between galaxies, dark matter, and gas, we may also learn more about the nature of gravity, dark energy, and the fabric of space-time itself. The cosmic web is not just a map of galaxies, but a living, breathing structure that holds the key to understanding the universe's past, present, and future. As we continue to explore the mysteries of the cosmic web, we are reminded of the vastness and complexity of the universe. This network of dark matter and gas filaments connects galaxies across unimaginable distances, shaping the structure of the cosmos and influencing the evolution of galaxies and stars. The cosmic web is not just a passive feature of the universe, it is a dynamic system that is constantly changing, evolving, and reshaping itself in response to the forces at play within it. Whether it continues to grow, fragment, or disassemble in the future, the cosmic web will remain a central feature of the universe for the foreseeable future, holding the secrets to some of the most profound mysteries of the cosmos. As we continue to explore the cosmic web, it's important to recognize that this vast structure is not just a static feature of the universe. It is a living, ever-evolving entity. The study of the cosmic web allows us to see the universe as a highly interconnected system, where galaxies, gas, and dark matter work together to create the intricate tapestry of the cosmos. However, the story of the cosmic web is still unfolding, and with every new observation, we uncover more about its behavior, dynamics, and the forces that shape it. The nature of the cosmic web itself has forced us to reconsider our understanding of the universe's architecture. Until recently, the universe was thought to be largely homogeneous, uniform throughout its vast stretches. Yet, the discovery of the cosmic web revealed that this idea was far from the truth. Instead of a smooth, evenly distributed cosmos, we now know that the universe is filled with vast voids, enormous galaxy clusters, and interconnected filaments of dark matter and gas. What makes this discovery so important is that it provides us with a framework for understanding the large-scale structure of the universe. Rather than looking at isolated galaxy clusters or individual galaxies, scientists now see the universe as a grand web of interconnected threads, each one contributing to the overall shape and structure of the cosmos. This shift in perspective has opened up new avenues for research, including the study of how galaxies form, evolve, and interact within the context of this larger structure. One of the most important questions that arises from the study of the cosmic web is how galaxies move within it. While the motion of individual galaxies is well understood, the movement of galaxies across the web presents new challenges. The filaments of the cosmic web act as highways that guide the motion of galaxies, but these highways are not static. As galaxies move along these cosmic highways, they are influenced by the gravitational pull of dark matter, gas, and other galaxies. This creates a dynamic and constantly changing landscape, where galaxies can form clusters, merge with other galaxies, or be pushed apart by the expansion of the universe. These movements are not random. Rather, they follow a predictable pattern that is determined by the structure of the cosmic web. Just as rivers carve out paths through the landscape, galaxies move along the filaments of the cosmic web, following the paths of least resistance. This process is incredibly slow, occurring over billions of years, but it has profound effects on the evolution of galaxies and the overall structure of the universe. At the intersections of these filaments, galaxy clusters are formed, and it is here that the most intense activity occurs. These clusters, often referred to as superclusters, are the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of galaxies, all bound together by the gravitational pull of dark matter. The interactions between galaxies in these clusters can be dramatic, with galaxies colliding, merging, and undergoing complex processes of star formation and gas accretion. As galaxies move along the cosmic highways, they encounter other galaxies and galaxy clusters. The gravitational pull between these objects can cause galaxies to merge, creating new, larger galaxies. This process of galaxy merging is one of the key ways in which galaxies grow and evolve. When two galaxies merge, their stars are often scattered, and the gas within the galaxies can collide, triggering intense bursts of star formation. This process is thought to be responsible for the creation of some of the most massive galaxies in the universe, as well as for the formation of supermassive black holes. But not all interactions between galaxies are so dramatic. In some cases, galaxies pass through each other without colliding. These so-called galaxy flybys are an important part of the dynamics of the cosmic web, as they can alter the trajectories of galaxies, pushing them onto different paths along the filaments of dark matter and gas. These interactions are less violent but still have a significant impact on the evolution of galaxies and the overall structure of the cosmic web. One of the most interesting features of the cosmic web is the role that gas plays in its formation and evolution. Gas is the fuel for star formation, and as gas flows along the filaments of the cosmic web, it cools and condenses, creating new stars and galaxies. The flow of gas is not uniform, and regions of higher gas density can lead to the formation of galaxy clusters, while regions of lower gas density can create vast voids in the cosmic web. The gas within the web is often heated to extremely high temperatures, particularly in the centers of galaxy clusters. This hot gas emits X-rays, which can be detected by telescopes such as the Chandra X-ray Observatory. These observations have provided us with a wealth of information about the behavior of gas within the cosmic web and its role in shaping the evolution of galaxies and clusters. As gas flows along the filaments of the cosmic web, it can also interact with dark matter, which forms the underlying structure of the web. Dark matter is invisible to telescopes, but its presence is inferred through its gravitational effects on visible matter. The interaction between gas and dark matter is still not fully understood, but it is believed that dark matter helps to channel gas along the filaments, guiding its movement and influencing the formation of galaxies and clusters. This interaction between gas and dark matter is one of the key factors that determines the overall structure of the cosmic web. In some regions, the gas and dark matter are in close contact, leading to the formation of dense galaxy clusters. In other regions, the gas and dark matter are more diffuse, creating vast voids where few galaxies exist. Another important feature of the cosmic web is the role of gravitational waves. These ripples in spacetime are generated by the acceleration of massive objects, such as merging black holes or neutron stars. Gravitational waves are difficult to detect, but recent advances in technology have allowed scientists to observe them for the first time. These observations are providing us with a new way to study the cosmic web and the interactions between galaxies, dark matter, and gas. Gravitational waves can also provide insights into the structure of the cosmic web itself. By studying the way these waves propagate through space, scientists can learn more about the distribution of mass in the universe and the behavior of dark matter. The detection of gravitational waves from distant galaxy clusters could provide important clues about the way these structures are connected within the cosmic web. In addition to gravitational waves, other forms of electromagnetic radiation, such as radio waves, can also be used to study the cosmic web. Observations of radio emissions from distant galaxies have revealed the presence of vast radio lobes that stretch across the cosmic web. These lobes are thought to be the result of powerful jets of energy emitted by supermassive black holes at the centers of galaxies. These jets can extend over vast distances, connecting galaxies and clusters within the cosmic web. By studying the radio emissions from these jets, scientists can gain new insights into the behavior of matter and energy within the cosmic web. These observations can also provide clues about the interactions between galaxies and dark matter, as well as the role of supermassive black holes in the evolution of the universe. As we continue to explore the mysteries of the cosmic web, it becomes clear that this vast structure is much more than just a collection of galaxies and dark matter filaments. It is a dynamic, interconnected system that is constantly evolving, shaping the universe in ways that we are only beginning to understand. From the movement of galaxies along cosmic highways to the role of gas and dark matter in the formation of galaxy clusters, the cosmic web holds the key to some of the most profound questions about the nature of the universe. In the coming decades, as our observational tools become more advanced, we will continue to uncover the secrets of the cosmic web. The discovery of new galaxy clusters, the detection of gravitational waves, and the mapping of dark matter will all help to deepen our understanding of the universe and its evolution. The cosmic web is a fundamental feature of the universe, and by studying it, we can gain a deeper insight into the forces that govern the cosmos. The mysteries of the cosmic web are far from solved, but with each new discovery, we are one step closer to understanding the true nature of the universe. The cosmic web may be vast, but it is also a testament to the interconnectedness of all things in the universe, from the smallest particles to the largest galaxy clusters. In the end, the study of the cosmic web is not just about understanding the structure of the universe, it is about understanding the very fabric of reality itself. As we continue our exploration into the cosmic web and its intricate structures, we must delve deeper into the mysteries that this vast cosmic highway holds. The cosmic web, after all, is not just a passive structure, it is a living, dynamic, and active network. Every galaxy, every cluster, every filament of dark matter and gas is a part of a grand design that is constantly evolving. It's a reminder of the scale and complexity of the universe, and how every piece of matter is interconnected in a delicate balance. The universe is not static, and neither are the cosmic highways. The interactions between galaxies and the forces at play in the cosmic web have far-reaching implications. One of the most intriguing aspects of these interactions is the way in which galaxies move along the dark matter filaments that comprise the cosmic web. This motion is not random or haphazard. Instead, it follows the gravitational pull of dark matter, which acts as the skeleton of the cosmic web. Dark matter's presence guides the flow of galaxies, and the influence it exerts helps to shape the structure of the universe. As we've mentioned earlier, the cosmic highways serve as conduits for galaxies to move along. But these highways are not just passive pathways, They are the result of an ongoing, dynamic interaction between matter, energy, and gravity. The gas that fills these highways is not just an empty void, but a conduit of energy. The behavior of this gas is governed by the interactions between particles, the influence of dark matter, and the processes that occur when galaxies move through these regions. Gas plays a crucial role in shaping the way galaxies evolve, and it does so through a process called gas accretion. This process involves the flow of gas into the centers of galaxies, fueling star formation and other cosmic phenomena. As galaxies move along the filaments of the cosmic web, they encounter regions of higher gas density, leading to the accretion of gas into their central regions. This process is responsible for the formation of new stars, the creation of supermassive black holes, and the evolution of galaxies over cosmic timescales. This interplay between galaxies and gas is not just confined to the filaments of the cosmic web, either. When galaxies collide or interact, they often release vast amounts of gas into the surrounding environment. This gas can then be channeled along the filaments, creating new pathways for galaxies to move through. In some cases, the collision of galaxies can trigger the formation of new galaxies altogether, as the gas that is released is compressed and condensed, leading to the creation of new stars. The role of dark matter in all of this is equally important. Dark matter, though invisible, exerts a gravitational influence on the visible matter in the universe. This gravitational pull shapes the structure of the cosmic web, creating the long, thin filaments that connect galaxy clusters. It's within these filaments that galaxies are most likely to form, as the dense regions of dark matter provide the gravitational pull necessary for the gas to condense and form new stars. Without dark matter, the cosmic web as we know it simply wouldn't exist. But dark matter does more than just hold the web together. It also plays a key role in shaping the motion of galaxies within it. The gravitational influence of dark matter affects the trajectory of galaxies as they move along the filaments. This influence can cause galaxies to cluster together, form larger structures, or even collide with other galaxies. Over time, these interactions create the large-scale structure of the universe, with galaxy clusters, superclusters, and voids all playing important roles in shaping the cosmic web. As we look further into the cosmic web, we begin to see how interconnected the universe truly is. Galaxies are not isolated objects but are instead part of a grand network, all bound together by the gravitational influence of dark matter. This interconnectedness is what gives the universe its structure, and it is what drives the evolution of galaxies over cosmic timescales. The cosmic highways, formed by the interaction of gas, dark matter, and galaxies, serve as the means by which matter flows throughout the universe, shaping the very fabric of space and time itself. Another key feature of the cosmic web that deserves further attention is the role of cosmic voids. These massive regions of empty space are just as important as the galaxy clusters and filaments in shaping the large-scale structure of the universe. The voids represent areas where the gravitational pull of dark matter is weaker, and as a result, they contain far fewer galaxies than the denser regions of the cosmic web. Despite their emptiness, cosmic voids play an important role in the dynamics of the universe. These voids serve as the vast gaps between the filaments of dark matter, and they are essential in maintaining the balance of the cosmic web. As galaxies move along the filaments, they can encounter these voids, which can cause them to change course or move in unexpected ways. The voids are not completely empty though, they are filled with a sparse distribution of dark matter, gas, and radiation, and these elements interact with the galaxies in complex ways. What's fascinating is that the voids are not truly empty. There is a kind of cosmic tension at play, where galaxies that lie at the edges of these voids can experience unusual gravitational effects. In some cases, galaxies in these regions can be pulled toward the filaments of the cosmic web, while in other cases, they are pushed away. This dynamic interaction between galaxies and voids is still not fully understood, but it is clear that the voids are not just empty space. They are essential in shaping the overall structure of the universe. Moreover, the discovery of cosmic voids has led to new insights into the role that dark energy plays in the expansion of the universe. As the universe continues to expand, the voids continue to grow, and the gravitational pull between galaxies weakens. This expansion is driven by the mysterious force known as dark energy, which causes the universe to accelerate outward. Understanding the nature of dark energy is one of the greatest challenges in modern cosmology, but the study of the cosmic web and the voids within it may hold the key to unlocking this mystery. The interplay between galaxies, gas, dark matter, and dark energy creates a complex and ever-changing landscape within the cosmic web. These interactions are responsible for the formation of galaxies, the clustering of matter, and the large-scale structure of the universe. The cosmic highways that connect galaxy clusters are more than just paths for galaxies to travel. They are the lifelines of the universe, guiding the motion of matter and shaping the cosmos in ways that we are only beginning to understand. The study of the cosmic web is still in its early stages, but every new discovery brings us closer to understanding the true nature of the universe. With each new telescope and observation, we gain new insights into the behavior of dark matter, the movement of galaxies, and the forces that shape the fabric of space and time. The cosmic web is a testament to the interconnectedness of all things in the universe, and as we continue to explore its mysteries, we will undoubtedly uncover new truths about the nature of reality itself. The cosmic highways that connect clusters of galaxies are not just pathways through the universe. They are the very structure of the universe, guiding the movement of matter and energy across vast distances. As we continue to study the cosmic web, we will undoubtedly uncover more about how these highways shape the evolution of galaxies, how they influence the formation of stars and black holes, and how they ultimately drive the evolution of the cosmos. The mysteries of the cosmic web are vast, and the journey to understand them is just beginning. The more we learn about the dark matter, gas, and galaxies that make up this intricate network, the closer we get to understanding the true nature of the universe. The cosmic highways are the key to unlocking many of the greatest mysteries of the cosmos, and with each new discovery, we get one step closer to revealing the secrets of the universe itself. The cosmic highways are not merely passive threads weaving through the fabric of space. They are active, dynamic pathways that hold the universe together. As we continue to investigate these cosmic filaments, we can't ignore the crucial role they play in shaping the large-scale structure of the universe. They are like the circulatory system of the cosmos, delivering and distributing matter, energy, and information across vast distances. Every filament, every node of matter, every galaxy cluster along these paths, tells a part of the greater story of the universe's evolution. One of the most profound implications of these cosmic highways is the interconnectedness of everything within the universe. While we often think of galaxies as isolated islands in space, they are actually part of a much larger, intricate web that links them across unimaginable distances. The highways that connect these galaxies aren't just pathways, they are the skeleton of the universe itself. The matter within them is not just arranged randomly but follows the specific, gravitationally influenced paths shaped by dark matter, gas, and the fundamental forces of the universe. To comprehend the structure of these cosmic highways, we need to revisit how galaxies form and evolve within the cosmic web. The first galaxies began to emerge after the Big Bang, a time when the universe was still in its infancy. As the universe cooled and matter began to clump together under the influence of gravity, the first stars and galaxies began to form. These early galaxies were not alone. They were surrounded by a vast, diffuse cloud of gas and dark matter, which provided the gravitational pull that helped them coalesce into the structures we see today. Dark matter, although invisible, plays an essential role in the creation and evolution of the cosmic web. It is the framework upon which galaxies and galaxy clusters form. Without dark matter, the gravitational pull necessary to hold these structures together would be insufficient. This dark matter is spread across the universe in vast, thin filaments that stretch across billions of light years. These filaments act as highways, guiding galaxies along their paths and allowing them to interact, collide, and grow over time. Gas is another critical component of the cosmic highways. The filaments of gas that run through the web are not just empty voids. They are filled with particles that interact in complex ways, driving the processes that govern star formation and the evolution of galaxies. Gas can be funneled into the centers of galaxies, where it can ignite the formation of new stars or feed supermassive black holes at the galactic centers. In many ways, the gas within the cosmic web acts as the lifeblood of the universe, fueling the creation of new stars, galaxies, and other cosmic phenomena. But while dark matter and gas may dominate the landscape of the cosmic highways, they are not the only forces at play. The expansion of the universe itself, driven by dark energy, also influences the dynamics of the cosmic web. Dark energy is a mysterious force that causes the universe to expand at an accelerating rate. As the universe grows larger, the distance between galaxy clusters increases, and the cosmic web stretches further out. This expansion affects the flow of galaxies and matter within the web, altering the way they interact and evolve over time. The interplay between dark matter, gas, and dark energy is a complex one, and it's only by studying these forces together that we can begin to understand the full scope of the cosmic web. Observing how galaxies move along these cosmic highways helps us not only track the evolution of the universe but also offers clues about the fundamental forces that govern it. One key observation about the cosmic highways is the way galaxies and galaxy clusters move along these paths. Galaxies are not fixed in place but are instead constantly moving under the influence of gravity. As galaxies move along the filaments of the cosmic web, they interact with one another in a variety of ways. Some galaxies collide, merging into larger galaxies, while others pass by one another, exchanging gas and matter along the way. These interactions are crucial in shaping the evolution of galaxies, triggering star formation and the creation of new cosmic structures. In addition to these mergers, another fascinating aspect of the cosmic highways is the role of cosmic shocks. When galaxies move through the gas-filled filaments of the cosmic web, they can create shock waves that travel through the gas. These shocks can trigger new star formation, create turbulent flows of gas, and influence the dynamics of the surrounding galaxy clusters. In some cases, these shocks can even create large-scale structures like the formation of hot gas halos around galaxy clusters, which are detectable through X-ray observations. As we dive deeper into the cosmic highways, we begin to uncover some of the most exciting and mysterious phenomena that occur within the cosmic web. One of the most intriguing aspects of these highways is the discovery of galaxy superclusters and the vast voids that separate them. Superclusters are massive collections of galaxies and galaxy clusters, and they are some of the largest structures in the universe. These superclusters are connected by the cosmic highways, forming the largest coherent structures known to humanity. However, while these superclusters are enormous in scale, they are not evenly distributed across the universe. Between them lie vast voids, regions of space that contain very few galaxies or other forms of matter. These voids are not empty in the strictest sense, but they are incredibly sparse compared to the dense regions of galaxy clusters and filaments that make up the majority of the cosmic web. The study of these voids is still in its early stages, but scientists have uncovered some fascinating properties of these vast, empty spaces. For example, researchers have observed that the voids are not simply areas of emptiness but contain subtle structures of their own. These voids can influence the movement of galaxies and gas, creating peculiar cosmic flows. Galaxies at the edges of voids, for example, can experience an effect known as the vacuum pull, where the gravitational forces from the surrounding matter cause them to move toward the denser regions of the cosmic web. In this way, the voids play a crucial role in shaping the motion of galaxies and galaxy clusters within the cosmic web. The study of the cosmic highways also holds promise for understanding the nature of dark energy, the mysterious force that is accelerating the expansion of the universe. Dark energy's influence is most apparent in the way it causes the universe to expand at an ever-increasing rate. As galaxies move along the cosmic highways, they are affected by both the gravitational pull of dark matter and the repulsive force of dark energy. The balance between these two forces is what determines the large-scale structure of the universe and its eventual fate. One of the key challenges in understanding the cosmic web is the fact that we can only observe a small portion of it at any given time. Even with the most advanced telescopes, our view of the universe is limited by the distance light can travel and the vast amount of time it takes for light to reach us. This means that the cosmic highways we observe today represent only a fraction of the entire cosmic web. To fully understand the structure of the universe, we need to continue developing new methods of observation and exploration. Advancements in technology, such as the development of more powerful telescopes and the study of gravitational waves, are providing us with new insights into the cosmic highways. These tools allow us to observe the motion of galaxies and the behavior of dark matter in greater detail, and they offer the potential for unlocking some of the deepest mysteries of the universe. As we continue to explore the cosmic web and the role of the cosmic highways in shaping the universe, we are reminded of the vastness and interconnectedness of all things in the cosmos. The highways that connect galaxy clusters are not merely paths through space. They are the threads that bind the universe together. They shape the formation of galaxies, drive the evolution of the cosmos, and guide the movement of matter across unimaginable distances. The cosmic web is still a mystery in many ways, but every new discovery brings us closer to understanding the intricate forces that govern the universe. Each observation, each new insight into the cosmic highways, helps us piece together the grand puzzle of the cosmos. It's a journey that will continue for generations to come, and the more we learn, the more we realize how much we still have to discover. As we continue to explore the mysteries of the cosmic highways, it's clear that they hold far more secrets than we can even begin to comprehend. These vast structures are the key to understanding the fundamental nature of the universe. Each filament of gas and dark matter is like a cosmic thread weaving together the entire structure of the cosmos. As we observe these highways, we're seeing the interplay between some of the most powerful forces in nature: gravity, dark energy, and dark matter, and how they interact to shape the universe on the largest scales. One of the more exciting avenues of research in this area is the way the cosmic highways may reveal more about the nature of dark matter. We've established that dark matter plays a crucial role in the formation of galaxy clusters and the cosmic web. But dark matter itself is an enigma. It doesn't emit light, nor can we detect it through traditional means. Instead, we infer its presence based on its gravitational effects on visible matter. The cosmic highways are prime locations for observing these effects. Because dark matter forms a substantial part of the mass within these cosmic highways, scientists are beginning to study how the distribution of this matter influences the behavior of the galaxies and clusters that traverse it. By analyzing the structure and movement of galaxies along these dark matter filaments, researchers can gain insights into the properties of dark matter itself. Is it made up of exotic particles that we've yet to detect? Does it interact with regular matter in ways we don't fully understand? These are just some of the questions we hope to answer by studying the cosmic web in more detail. In addition to studying dark matter, we must also consider the role that cosmic magnetic fields play in shaping the cosmic highways. These magnetic fields are not only found within individual galaxies or stars but also stretch across vast distances within the cosmic web. These fields are believed to influence the motion of charged particles, the behavior of gas clouds, and the flow of matter within the cosmic filaments. Though magnetic fields on such large scales are notoriously difficult to detect, new observational techniques and models are beginning to shed light on their role in the cosmic landscape. Recent studies have also suggested that the cosmic highways are not static. They may actually be evolving over time. As galaxies interact with one another and move along the filaments of the cosmic web, they influence the properties of these highways. The gas within the filaments can be compressed or heated, triggering star formation or causing the gas to cool and collapse into dense regions. These processes can reshape the structure of the cosmic web, creating new pathways for galaxies to follow and altering the way the universe evolves. In this sense, the cosmic highways are alive, constantly changing and reshaping themselves in response to the forces acting upon them. There's also the question of whether these cosmic highways could provide answers to some of the universe's deepest questions. Could they offer clues about the nature of the Big Bang itself, or how the universe will end? The structure of the cosmic web may contain information about the early universe, moments after the Big Bang, when the first filaments of gas and dark matter began to form. By studying the way these highways have evolved, scientists may be able to trace the history of the universe back to its very beginning, offering new insights into the origins of space and time. On the other hand, the cosmic highways might also hold clues about the ultimate fate of the universe. As the universe continues to expand, galaxies move further apart from one another, and the dark energy that drives this expansion grows more dominant. Some scientists theorize that this expansion could eventually tear apart the cosmic web itself, causing galaxies to drift farther and farther away from each other until they are completely isolated. This scenario, known as the Big Rip, is just one possible fate for the universe, and the cosmic highways may offer vital clues about whether or not this is a reality. Another compelling aspect of the cosmic highways is how they might connect to the larger question of the multiverse. The concept of a multiverse suggests that our universe is just one of many, each with its own set of physical laws and properties. The idea of the multiverse has been proposed as a solution to some of the most perplexing questions in cosmology, such as why the laws of physics appear to be fine-tuned for life. If the cosmic highways are indeed connected to the broader structure of the universe, could they also be connected to other universes within a larger multiversal framework? This remains a speculative question, but the discovery of such connections, if they exist, could have profound implications for our understanding of reality. Moreover, as we look deeper into the cosmic highways, it's clear that there's much more to discover about the role of supermassive black holes and their relationship with galaxy clusters. Supermassive black holes, which lie at the centers of many galaxies, exert a powerful influence on the galaxies and galaxy clusters around them. These black holes can influence the flow of gas and the formation of new stars, and they are believed to play a critical role in the growth of large-scale structures in the universe. Understanding how supermassive black holes interact with the cosmic highways could provide new insights into how galaxies evolve and how large-scale structures form over time. One of the most intriguing phenomena we've encountered in our exploration of the cosmic highways is the idea that these filaments could be sites of extreme astrophysical events. For instance, as galaxies move along these highways, they could experience intense gravitational interactions, leading to the formation of new stars, the fueling of black holes, or the eruption of powerful jets of energy. These events could release vast amounts of energy and matter into the surrounding environment, reshaping the structure of the cosmic web and influencing the galaxies that lie along the highways. The study of these energetic processes is not only exciting for our understanding of cosmic evolution, but also for the potential they offer in terms of astrophysical observations. Cosmic highways, with their high concentrations of gas and dark matter, may be the ideal places to observe some of the most extreme and high-energy phenomena in the universe, such as gamma-ray bursts or supernovae. By studying these events, we can gain a better understanding of how galaxies and galaxy clusters evolve and the role that extreme astrophysical processes play in shaping the universe. It's also worth noting that our understanding of the cosmic highways is still in its early stages. While we've made tremendous progress in observing and studying these structures, there's still much we don't know. New tools and technologies, such as advanced telescopes and simulations, are helping scientists uncover more details about the cosmic web, but the true nature of these highways remains elusive. The study of the cosmic web is one of the most exciting and active areas of research in modern astrophysics, and as we continue to explore it, we are likely to make even more groundbreaking discoveries. As we look forward to the future of cosmic research, we must also consider how these highways might help us answer some of the most fundamental questions about the universe. How did the universe come to be in its current form? What will be its ultimate fate? And are there other universes, or dimensions, that lie beyond the cosmic web? These are just some of the questions that scientists are hoping to answer by studying the cosmic highways and the cosmic web. The answers may be far beyond our current understanding, but by continuing to study these cosmic structures, we are one step closer to unlocking the greatest mysteries of the universe. In the grand scheme of things, the cosmic highways are more than just fascinating scientific phenomena. They are the pathways to understanding our place in the universe. As we look up at the stars, we are not just gazing at isolated points of light in the sky. We are looking at a vast and interconnected web of galaxies, clusters, and filaments that span the entire universe. The cosmic highways are the threads that bind everything together, and through their study, we may one day come to understand the deepest truths of the cosmos. As we continue to unravel the mysteries of the cosmic highways, one of the most profound implications of this research lies in the potential for understanding the very fabric of space-time. The connections between galaxy clusters and the vast webs of gas and dark matter that thread them together offer a unique glimpse into the gravitational forces that govern the universe. These cosmic highways are not just random features in the cosmic landscape but rather vital structures that help define the large-scale architecture of the universe itself. At the heart of these cosmic highways lies dark energy, a mysterious force driving the accelerated expansion of the universe. While dark energy's exact nature remains one of the biggest puzzles in modern cosmology, its influence on the structure of the universe is undeniable. The dark energy that propels the expansion of the universe also influences how galaxies and galaxy clusters are distributed along these cosmic filaments. As the universe continues to expand, the matter within these highways is being stretched, leading to an ever-increasing distance between galaxy clusters. But this expansion is not uniform. Instead, it happens along the filaments, giving rise to a dynamic interplay between gravity and dark energy. Understanding this relationship could provide crucial insights into the future of the universe and its ultimate fate. This dynamic nature of the cosmic web has a significant impact on our theories about the evolution of the universe. If we are to understand the formation of galaxy clusters and the vast networks of filaments that connect them, we must study the forces shaping these structures. One of the key components in this study is understanding the role of gas within the filaments of the cosmic web. This gas is primarily composed of hydrogen and helium, and though it is much less dense than the gas found within galaxies, it still plays a crucial role in the evolution of large-scale cosmic structures. As gas moves along the filaments, it can experience shock waves and intense gravitational interactions that influence the formation of new galaxies. Some of this gas may eventually collapse to form new stars or even entire galaxies, creating new pockets of matter within the cosmic web. In other cases, the gas may be expelled from clusters or be heated to extremely high temperatures by the gravitational forces within the filaments. These processes contribute to the dynamic and ever-changing nature of the cosmic highways. Furthermore, the study of cosmic gas offers valuable insights into the behavior of matter on the largest scales. By examining how this gas flows along the filaments and how it interacts with dark matter and dark energy, scientists can learn more about the fundamental forces governing the universe. This knowledge could help refine our understanding of how galaxies form, evolve, and interact over time, shedding light on the processes that give rise to the universe's vast structures. As our understanding of the cosmic highways deepens, we are also discovering new ways to explore them. Advances in observational technology, such as more powerful telescopes and advanced imaging techniques, are allowing scientists to peer deeper into the heart of the cosmic web than ever before. One such technique, known as gravitational lensing, has proven particularly useful in studying the cosmic highways. Gravitational lensing occurs when the light from distant objects is bent and magnified by the gravitational pull of massive structures like galaxy clusters. By studying the way light is distorted as it passes through these cosmic filaments, astronomers can map the distribution of dark matter and gas in these structures, providing valuable clues about the shape and behavior of the cosmic web. Another exciting development in cosmic research is the use of simulations to model the behavior of the cosmic web. These simulations use sophisticated computer models to replicate the behavior of dark matter, gas, and galaxies as they move along the cosmic highways. By running these simulations, scientists can test different hypotheses about the formation and evolution of the cosmic web, gaining a better understanding of how large-scale structures evolve over time. These simulations also help identify the areas of the cosmic web that are most likely to contain the most significant concentrations of matter, enabling astronomers to focus their observations on the most promising regions of the universe. One of the most remarkable aspects of the cosmic highways is the possibility that they could harbor the answers to some of the most profound questions in science. If we could observe the interactions between dark matter, dark energy, and ordinary matter along these filaments, we might be able to uncover clues about the nature of the universe itself. For example, do these filaments hold the key to understanding the mysterious origins of dark matter? Could the cosmic highways provide evidence for the existence of other dimensions or parallel universes? These are just some of the questions that researchers are actively investigating as they study the cosmic web. Moreover, The exploration of cosmic highways might help address the ultimate fate of the universe. Will the universe continue to expand indefinitely, as dark energy pushes galaxies apart, or will it eventually collapse back in on itself in a big crunch? The structure of the cosmic web, with its intricate network of filaments and clusters, may hold the key to answering this question. By studying how the cosmic highways evolve over time, scientists can gain valuable insights into the long-term behavior of the universe and how it might end. Some models suggest that the universe will continue to expand at an ever-increasing rate, eventually leading to a scenario known as the Big Freeze, in which galaxies drift farther and farther apart until all stars burn out and the universe becomes cold and dark. Others propose that the universe could eventually contract, leading to a dramatic collapse that would reverse the process of cosmic expansion. The cosmic highways may provide clues that could help determine which of these outcomes is most likely. As we peer further into the universe, it becomes increasingly clear that the cosmic highways are not merely structures to study for their own sake. They are crucial pieces of the cosmic puzzle. They are the bridges that connect galaxies across the vast distances of space, and in doing so, they offer a glimpse into the larger forces that shape the universe. Whether we are studying dark matter, gas, dark energy, or the evolution of cosmic structures, the cosmic highways provide an unparalleled opportunity to explore the most fundamental questions of science. In addition to their scientific value, the study of cosmic highways also has profound philosophical implications. The realization that the universe is interconnected on such large scales challenges our understanding of space, time, and existence. The very concept of a cosmic web, with its intricate network of filaments and clusters, invites us to reconsider our place in the universe. Are we simply isolated beings in a vast and chaotic cosmos, or are we part of a larger, interconnected whole that transcends our understanding of space and time? The study of the cosmic highways opens up new avenues for exploring these existential questions, offering a deeper sense of wonder and awe at the mysteries of the universe. While the cosmic highways may seem like distant, abstract concepts, they are ultimately an invitation to explore the deepest aspects of reality. They are not just distant structures floating in the void. They are part of a larger cosmic story that is still unfolding. As we continue to probe these vast structures, we are not only uncovering the mysteries of the universe but also learning more about our place within it. The cosmic highways are not just highways across space. They are pathways to understanding the fundamental nature of reality itself. As we continue to explore these cosmic highways, it's essential to understand the fundamental components that make them possible. The most dominant force responsible for the formation and structure of the cosmic web is gravity. Gravity not only pulls matter together, forming galaxies and galaxy clusters, but also shapes the cosmic highways through its influence on dark matter and gas. These forces work in tandem to create vast, interconnected structures that extend across the universe, far beyond what the naked eye can see. Dark matter, which makes up a significant portion of the universe's total mass, plays an essential role in these cosmic highways. Although it does not emit or interact with electromagnetic radiation, meaning we can't see it directly, dark matter exerts gravitational forces on visible matter. It is theorized to be the glue that holds galaxies together, keeping them from flying apart due to their high velocities. When we look at the cosmic web, dark matter is present in the form of invisible filaments, stretching and bending through space in ways that shape the paths along which galaxies travel. These dark matter structures are not static. They evolve and shift over time, forming ever-changing highways that continue to grow and stretch across the universe. Alongside dark matter, gas, primarily in the form of hydrogen and helium, fills the vast expanse of the cosmic web. While dark matter forms the underlying structure, gas flows along the filaments, acting as a fluid component that helps to connect different parts of the universe. This gas is often incredibly hot and diffuse, but its presence is essential to the dynamics of the cosmic web. It is along these gas-filled filaments that galaxies move, merge, and form new stars. The gas, heated by the gravitational forces within the filaments, can reach millions of degrees, creating a hot and dynamic environment that plays a significant role in the evolution of the universe. The interactions between gas and dark matter create a delicate balance that shapes the cosmic web. The gas is carried along by the dark matter, with both interacting in complex ways. The gravitational forces exerted by the dark matter help direct the flow of gas, influencing how it accumulates, heats up, or even dissipates over time. These interactions lead to the formation of galaxy clusters, the most massive structures in the universe, which act as cosmic hubs within the web. The gas present within these clusters can emit X-rays, providing us with a glimpse into their extreme environments and helping scientists map out the locations and movements of cosmic highways. The role of dark energy in shaping the cosmic web is equally crucial. While gravity pulls matter together, dark energy, which is responsible for the accelerated expansion of the universe, pushes against the fabric of space-time. This cosmic push causes the distances between galaxy clusters to increase over time. The cosmic highways, therefore, are not static. They are being stretched as the universe expands. However, despite this stretching, the structures of the cosmic web are not torn apart. Instead, they evolve, with new filaments and connections forming as the universe grows larger. Dark energy is the force that drives this expansion, pushing galaxies further apart, but at the same time, its effects are felt within the cosmic web, creating a dynamic, constantly changing landscape. One of the most fascinating aspects of the cosmic highways is how they are observed. For centuries, astronomers could only study galaxies individually, but with the advent of modern telescopes and imaging techniques, we can now observe the universe on a much larger scale. Using tools like the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers have been able to capture stunning images of the cosmic web, revealing the intricate structures of dark matter, gas, and galaxies. These observations are vital for understanding how the cosmic web works and how the forces of gravity, dark energy, and dark matter interact to shape the universe. The study of the cosmic web also relies heavily on simulations and computational models. Scientists use complex computer algorithms to recreate the interactions between dark matter, gas, and galaxies, allowing them to test different theories and hypotheses about the universe's evolution. These simulations have revealed many surprising results, such as the way in which galaxy clusters move and interact over time. They also help scientists predict how the cosmic web will evolve in the future, providing crucial insights into the fate of the universe. These simulations have proven to be invaluable in understanding the growth and formation of cosmic highways. By simulating the movement of dark matter, gas, and galaxies, researchers can visualize how the cosmic web evolves over billions of years. The results have shown that the cosmic web grows in a self-similar pattern, with new structures forming as smaller filaments, and clusters merge to create larger ones. This process, known as hierarchical structure formation, is a key feature of the universe's evolution. It suggests that, over time, the cosmic highways will continue to grow and expand, forming a vast and interconnected network of galaxies, dark matter, and gas. As we look ahead, one of the most exciting aspects of studying the cosmic highways is the potential for new discoveries. The cosmic web is still largely unexplored, and there are many unanswered questions about how it functions. For example, how do galaxy clusters form and evolve within these filaments? What role does the cosmic web play in the formation of new stars and galaxies? Could the cosmic highways hold clues to the nature of dark matter and dark energy, two of the biggest mysteries in modern physics? To answer these questions, astronomers are developing new technologies and techniques to probe deeper into the heart of the cosmic web. One promising approach is the use of gravitational lensing, which allows scientists to observe the bending of light as it passes through massive structures like galaxy clusters. By studying the way light is distorted, researchers can map the distribution of dark matter and gain a better understanding of the forces at play within the cosmic web. Another exciting development is the creation of ultra-sensitive telescopes that can detect faint signals from the gas within the cosmic web. These signals, which include X-rays and radio waves, offer valuable insights into the temperature, density, and movement of the gas, providing crucial data for understanding the evolution of the cosmic highways. In addition to these technological advancements, the growing field of multi-messenger astronomy is opening up new ways of studying the universe. By combining observations from different types of radiation, such as gravitational waves, electromagnetic waves, and neutrinos, astronomers are able to gain a more complete picture of the cosmic web and its role in the universe's evolution. This interdisciplinary approach has already led to groundbreaking discoveries, and it is expected to provide even more insights into the mysteries of the cosmic highways in the years to come. The study of cosmic highways not only helps us understand the universe's structure but also challenges our understanding of fundamental physics. As scientists delve deeper into the intricate web of galaxies, dark matter, and gas, they are uncovering new clues about the nature of space-time, gravity, and the forces that govern the universe. These insights are reshaping our understanding of the cosmos, and could eventually lead to the discovery of new physical laws that govern the universe on the largest scales. As our knowledge of the cosmic web continues to grow, so too does our appreciation for the vastness and complexity of the universe. The cosmic highways are not just lines on a map of the universe. They are dynamic, evolving structures that connect galaxies across unimaginable distances. By studying these highways, we are gaining a deeper understanding of the universe's past, present, and future. They remind us of the vastness of space and the incredible forces that shape the universe, leaving us with more questions than answers but also with the knowledge that we are only beginning to scratch the surface of this profound mystery. Ultimately, the exploration of the cosmic highways is a journey into the unknown. It is a journey that will take us to the farthest reaches of the universe, where dark matter, gas, and galaxies intertwine in a complex, ever-evolving web. As we continue to study these structures, we will uncover more about the forces that shape our universe, the nature of the cosmic web itself, and our place in the grand scheme of things. The cosmic highways are a testament to the interconnectedness of all things in the universe, and they hold the promise of even greater discoveries in the years to come. As we continue our exploration of the cosmic highways, the next frontier lies in understanding how these vast interconnected structures influence the movement and growth of galaxies themselves. This interconnected web of dark matter and gas does not merely act as a passive conduit between distant galaxy clusters. It plays an active role in shaping the dynamics of these galaxies over time. One of the most fascinating aspects of these galactic highways is the way they guide the migration and mergers of galaxies. Galaxies are not fixed. They move through space, and much like particles flowing in a stream, they follow the gravitational pull of the dark matter that defines the structure of the cosmic web. This movement is not random. It's directed by the filamentary network that spans the universe, which serves as a cosmic roadmap for galaxies, guiding them along specific pathways toward one another. Over billions of years, these galaxies have collided and merged, forming the supermassive galaxy clusters that we observe today. The cosmic highways are essential for this process, directing galaxies towards the most massive and dense regions of the universe, where the largest galaxy clusters reside. These collisions, while appearing violent from our perspective, are crucial for the long-term evolution of galaxies. When two galaxies collide, their gas and dust interact, triggering the formation of new stars. These cosmic highways, as highways of motion and interaction, guide galaxies toward these productive collisions, fueling the creation of new cosmic structures. But what about the dark matter? While dark matter is invisible and doesn't emit light, it plays a significant role in the gravitational interaction that drives these collisions. The dark matter within galaxy clusters, for example, often forms a dense core around which galaxies spiral and merge. This dark matter is the unseen architect of these massive galactic collisions, shaping the final outcome of these cosmic dances. Now, consider the dark energy component of this cosmic web. While dark energy is largely responsible for the accelerated expansion of the universe, it also exerts subtle forces on the way these cosmic highways evolve. Imagine, if you will, that as the universe expands, the filaments of dark matter and gas within the cosmic web stretch as well. However, they do not stretch at the same rate as the galaxies they contain. This differential stretching can have profound consequences for the future of galaxy clusters, as the cosmic web grows ever thinner in some regions, and more dense in others. Dark energy's influence on the cosmic web is still not fully understood, but it plays an essential role in how the universe continues to evolve. Its constant push against gravity has far-reaching implications for the movement of galaxies and the structure of the cosmic highways that connect them. Further investigations into the cosmic highways have also revealed the mysterious phenomena of voids, or areas in the cosmic web where little matter exists. These vast empty regions are just as critical to the overall structure of the universe as the dense filaments of dark matter and gas. While voids are often thought of as the empty spaces between galaxies, they are not devoid of activity. The gas within voids is typically very diffuse, but it is still gravitationally connected to the rest of the cosmic web. The voids also influence the behavior of galaxies and clusters in unexpected ways. For example, galaxies located near the edges of voids may experience different gravitational interactions than those located within dense filaments. Voids also shape the expansion of the universe, as they provide areas where galaxies and clusters can drift apart as dark energy continues to accelerate the expansion of space. To truly appreciate the scale and complexity of these cosmic highways, it is necessary to step back and consider their role in the broader context of the universe. The cosmic web, with its filaments and voids, is not just a structural feature of the universe. It is a dynamic, evolving system that is constantly being shaped by the forces of gravity, dark matter, and dark energy. It is a testament to the intricate and interconnected nature of the cosmos, a realization that everything in the universe, from the smallest subatomic particles to the largest galaxy clusters, is part of a vast, interconnected network. Yet, as grand as this web of matter and energy appears, there is still much that we do not know. The cosmic highways are full of mysteries, and while we have learned much about their structure and function, many questions remain unanswered. For instance, how does the presence of dark energy influence the formation of new cosmic structures? What role do these highways play in the eventual fate of the universe? Will the expanding cosmic web eventually reach a point where the galaxy clusters are so spread out that the cosmic highways themselves will fade away? These questions, though profound, are a testament to the complexity and wonder of the universe. They point to the limits of our current understanding and open the door to new avenues of research and discovery. To answer them, scientists are developing increasingly sophisticated tools and techniques, such as next-generation telescopes, advanced simulations, and theoretical models, which will provide us with deeper insights into the nature of the cosmic highways and the forces that govern them. As we continue to look outward into the depths of the universe, the study of these cosmic highways has a far-reaching impact on how we understand the universe as a whole. Not only does it challenge our perceptions of the structure of space-time, but it also forces us to confront some of the most fundamental questions in cosmology. Why do cosmic structures form in the way that they do? What is the ultimate fate of the universe? And how will the cosmic web evolve in the billions of years to come? Understanding the cosmic highways is not just about answering these questions. It is also about redefining our place in the cosmos. For all of human history, we have looked up at the stars and wondered about the vastness of the universe. Now, as we delve deeper into the mysteries of the cosmic web, we are beginning to understand the intricate forces that bind the universe together. We are learning how galaxies and clusters move, how dark matter and dark energy shape the fabric of space, and how cosmic highways connect distant corners of the universe in ways we never imagined possible. This journey, this quest to uncover the secrets of the universe's structure, is far from over. As our tools improve and our understanding deepens, we will continue to push the boundaries of knowledge. The cosmic highways, with all their complexities, will continue to reveal their secrets, one by one. And with each discovery, we move closer to answering some of the most profound questions humanity has ever asked. The exploration of cosmic highways is not just a scientific endeavor, it is a reflection of our insatiable curiosity and desire to understand the universe in which we live. As we venture further into the depths of space, we are not only uncovering the mysteries of distant galaxies and clusters, we are also exploring the very nature of reality itself. The cosmic highways are a reminder of the vastness, complexity, and interconnectedness of the universe, a universe that is still full of secrets waiting to be discovered. And as we look to the future, it is clear that the study of these highways will continue to be a central focus of scientific inquiry. With each new discovery, we move closer to unraveling the mysteries of the cosmos, and with each answer, we are presented with even more questions. This endless cycle of discovery and exploration is what drives us forward, propelling us toward new frontiers of knowledge and understanding. And perhaps, as we unlock the secrets of the cosmic highways, we will ultimately come to understand our place in the universe in ways we never thought possible. As we continue our journey through the cosmic web, it's crucial to consider not just the galactic highways and their influence on the motion of galaxies, but also the broader picture of how these structures affect the evolution of the universe as a whole. We have seen that the filaments of dark matter, gas, and even dark energy are intricately intertwined, forming a web that dictates the fate of galaxies, clusters, and the very fabric of space-time. But what happens when we zoom out even further? One of the more captivating aspects of the cosmic web is how it reveals the underlying principles of cosmic evolution. The web is not a static entity. Rather, it is constantly changing, growing, and evolving, shaped by the fundamental forces that govern the universe. The expansion of the universe, driven by dark energy, is perhaps the most profound influence on the cosmic web. As space itself stretches, the filaments that connect galaxy clusters are also stretched, causing the distances between galaxies to increase. This process, known as cosmic expansion, has been ongoing since the Big Bang, and its effects are felt across the entire cosmic web. Yet, as the universe continues to expand, this expansion is not uniform. There are regions where the fabric of the cosmic web is more tightly stretched, and regions where it is looser. These variations in the expansion rate are not just a matter of distance, they also affect the formation of new cosmic structures. For instance, areas where the cosmic web is denser, such as near galaxy clusters, will continue to evolve in ways that promote the formation of new galaxies, stars, and other cosmic bodies. In contrast, regions of lower density may experience a more gradual evolution, with fewer new structures forming. This uneven distribution of matter and energy is one of the driving forces behind the ongoing evolution of the universe. However, cosmic expansion is not the only factor at play. The interplay between gravitational forces and dark energy also plays a crucial role in determining how the cosmic web evolves over time. Gravitational interactions, particularly the gravitational pull of dark matter, are responsible for the formation of galaxy clusters. As galaxies move along the cosmic highways, they are drawn toward these regions of higher density, where the gravitational pull is stronger. This leads to the formation of superclusters, vast structures composed of thousands of galaxies bound together by gravity. These superclusters are some of the largest structures in the universe, and they represent the ultimate expression of the cosmic web's influence on the formation of cosmic structures. But even within these superclusters, the forces of dark energy and dark matter are at work, guiding the motion and growth of galaxies. As dark energy continues to drive the expansion of the universe, it is causing galaxies to move away from each other at an increasingly rapid rate. However, within the dense regions of superclusters, the gravitational forces are strong enough to counteract this expansion, leading to the formation of even more massive structures. In this way, the cosmic web not only guides the motion of galaxies but also shapes the very architecture of the universe itself. It is important to note that while these cosmic highways are crucial for the formation and movement of galaxies, they are also key players in the larger-scale structure of the universe. The cosmic web serves as a framework that holds the universe together, providing a structure within which galaxies, clusters, and superclusters can evolve. Without these highways of dark matter and gas, the universe would lack the interconnectedness that makes it possible for galaxies to form, evolve, and interact. But there is another fascinating aspect to the cosmic web that we have yet to fully explore: the role of cosmic voids in shaping the universe. These vast, empty regions between galaxies and clusters are not just empty spaces, they are integral components of the cosmic web. The voids play an essential role in the distribution of matter and energy in the universe, and they influence the behavior of galaxies in profound ways. Voids are not empty in the strictest sense. While they contain very low densities of matter compared to the filaments of the cosmic web, they still contain gas, dust, and dark matter. The gravitational influence of these voids is significant, particularly when it comes to the movement of galaxies. For instance, galaxies located near the edges of voids experience less gravitational pull from nearby galaxies and clusters, which can affect their motion and interactions. This phenomenon, known as the void effect, can influence the trajectory of galaxies and even lead to the formation of isolated galaxies in these regions. Voids are also important in the study of dark energy. As we mentioned earlier, dark energy is driving the accelerated expansion of the universe, and its effects are most pronounced in the voids. Because voids contain less matter, they are more sensitive to the influence of dark energy. This means that the expansion of the universe is felt more strongly in these regions, causing them to stretch and grow at a faster rate than more densely populated areas. The study of voids is therefore crucial for understanding how dark energy is shaping the future of the universe. One of the most intriguing aspects of voids is how they affect the distribution of galaxies. While the filaments of the cosmic web form a dense, interconnected network of matter, the voids create vast spaces between these structures. This separation is not just a matter of distance, it also influences the movement of galaxies. As galaxies move along the cosmic highways, they are naturally drawn toward the denser regions of the universe, the filaments and clusters of dark matter and gas. However, the voids act as barriers, creating regions where galaxies are less likely to be found. This distribution of galaxies is one of the key features of the cosmic web, and it has profound implications for our understanding of the universe's large-scale structure. In many ways, the study of voids is just as important as the study of the filaments themselves. While the filaments are where the majority of the matter in the universe is concentrated, the voids represent the regions where the universe is expanding most rapidly. By studying these voids, scientists can gain a deeper understanding of the role of dark energy in the universe's expansion and how it is influencing the formation of cosmic structures. As we continue to probe the depths of the cosmic web, one thing becomes clear: the universe is far more interconnected and dynamic than we could have ever imagined. From the vast highways of dark matter and gas that connect galaxy clusters to the empty voids that shape the distribution of matter, the cosmos is a constantly evolving, intricate web of structures and forces. These cosmic highways are not just pathways for galaxies, they are the very foundation of the universe itself. Looking forward, the future of cosmic exploration holds even more exciting possibilities. With advancements in technology and new observational techniques, we will be able to explore these cosmic highways in greater detail than ever before. We are already beginning to glimpse the true scale of the universe's large-scale structure, and as our understanding deepens, so too will our ability to unravel the mysteries of the cosmic web. What we know today is just the beginning. As we venture further into the universe, we will uncover even more about the nature of dark matter, dark energy, and the fundamental forces that shape our reality. The cosmic highways, with all their complexity and wonder, will continue to guide us on this journey of discovery. And who knows what new insights await us as we venture into the farthest reaches of space, seeking to understand the true nature of the universe and our place within it? The cosmic web is more than a structural framework of the universe. It's a story of connections and interactions that have shaped everything we see, including our very existence. These vast intergalactic highways are both the birthplace and conduit of cosmic phenomena, creating patterns in the universe that echo through time and space. As we look deeper into the fabric of the cosmos, the role of these highways becomes even more fascinating. Take, for example, the interaction between dark matter and ordinary matter. Dark matter, invisible and enigmatic, forms the backbone of the cosmic web, dictating where filaments form and how they connect clusters. This unseen material exerts a gravitational pull that attracts ordinary matter, gases, stars, and galaxies, into these filaments, creating the luminous threads of the cosmic web we can observe. In these intersections, or nodes, where highways converge, the densest regions of matter in the universe form. These nodes are the seats of galaxy clusters, where thousands of galaxies swirl around each other, held together by immense gravitational forces. The interplay between the filaments and nodes demonstrates how interconnected the universe truly is. Every galaxy cluster owes its existence to the web, and every filament plays a role in shaping the vast expanse of cosmic structures. But what makes these filaments, and nodes. Even more remarkable is their influence on star formation. The gas within the filaments often acts as a reservoir for the raw materials needed to birth stars. As galaxies move along these intergalactic highways, they interact with the gas, sometimes stripping it away and fueling star formation in the process. This interaction is crucial for understanding how galaxies evolve over billions of years and how the universe itself matures. At the same time, these highways reveal a story of cosmic migration. Galaxies don't just sit still, they move, often following the pathways carved by the cosmic web. This migration is not random, it's guided by the gravitational pull of the web's filaments. Over time, this movement has shaped the distribution of galaxies across the universe, forming intricate patterns that scientists can map and study. These patterns tell a story of cosmic history, showing us how the universe has expanded and evolved since the Big Bang. However, the highways are not uniform. They vary in density, composition, and behavior, leading to diverse phenomena. Some regions of the cosmic web are rich in gas, fostering the birth of new stars and galaxies. Others are dominated by dark matter, creating invisible but powerful gravitational wells. These variations are crucial for understanding why certain regions of the universe appear as they do, and why some areas are teeming with activity while others remain relatively quiet. The filaments themselves are not static, they flow and shift over time. This movement is influenced by the overall expansion of the universe, as well as local gravitational interactions. As galaxies and gas move along these highways, they interact with one another in complex ways. Collisions between galaxies, for instance, can lead to the formation of entirely new structures, such as starburst regions where intense star formation occurs. These interactions are a testament to the dynamic nature of the cosmic web. Adding to the complexity is the role of feedback mechanisms, particularly from active galactic nuclei, AGN, and supernovae. These energetic events can expel gas from galaxies, enriching the filaments with heavy elements and altering the flow of matter. This feedback loop is a critical aspect of cosmic evolution, as it regulates star formation and redistributes matter across the web. In recent years, observations using advanced telescopes have provided unprecedented insights into these processes. Instruments like the James Webb Space Telescope and large-scale surveys of the universe have allowed scientists to map the cosmic web with incredible precision. These maps not only reveal the structure of the web but also highlight regions of active star formation, galaxy mergers, and other dynamic events. Through these observations, we are beginning to piece together the puzzle of how the universe's largest structures came to be. One particularly intriguing aspect of these observations is the role of magnetic fields in shaping the cosmic web. While often overlooked, magnetic fields are present throughout the universe and can influence the behavior of gas and particles within the filaments. These fields may help regulate the flow of matter along the highways, acting as an invisible force that shapes the dynamics of the web. Understanding these magnetic fields is a key area of research, as it could provide new insights into the processes driving cosmic evolution. Another area of interest is the interaction between the cosmic web and dark energy. While dark matter forms the skeleton of the web, dark energy is the force driving its expansion. This interaction creates a delicate balance that shapes the universe on the largest scales. As the universe continues to expand, the filaments of the cosmic web are stretched, and their influence on the motion of galaxies evolves. This interplay between dark matter and dark energy is one of the most profound mysteries in cosmology, and studying it could unlock answers to fundamental questions about the nature of the universe. Furthermore, the cosmic web serves as a laboratory for understanding the origins of cosmic structure. By studying the web, scientists can trace the history of the universe back to its earliest moments. The patterns we see today are the result of billions of years of cosmic evolution, shaped by the initial conditions of the Big Bang. These patterns are imprinted in the cosmic microwave background radiation, the faint afterglow of the Big Bang, and serve as a record of the universe's infancy. Even as we uncover more about the cosmic web, many questions remain. For instance, what role do cosmic highways play in the formation of supermassive black holes? These enigmatic objects are found at the centers of most galaxies, but their origins and growth are still not fully understood. The filaments of the cosmic web may provide a pathway for gas and matter to flow into these black holes, fueling their growth and influencing their behavior. Similarly, the role of cosmic highways in the distribution of dark matter is an ongoing area of research. While we can observe the effects of dark matter through its gravitational pull, its exact nature remains elusive. By studying the filaments of the cosmic web, scientists hope to gain a better understanding of dark matter's properties and its role in the universe. The more we learn about the cosmic web, the more we realize how interconnected everything in the universe truly is. These highways are not just pathways for matter, they are the threads that weave the fabric of the cosmos. They connect galaxies, clusters, and even the voids, creating a unified structure that underpins the entire universe. In the end, the cosmic web is a testament to the beauty and complexity of the universe. It reminds us that even the largest structures in existence are part of a larger whole, bound together by invisible forces and shaped by the interplay of matter and energy. As we continue to explore these intergalactic highways, we are not just uncovering the secrets of the universe, we are also gaining a deeper understanding of our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.